Hello and welcome to Sleepy Science. I'm so glad you've arrived. Maybe your day has been long, your thoughts a little tangled. Or maybe you're simply here because something deep inside you still wonders what the universe is really made of. Tonight, we won't be racing through facts or equations. We'll be drifting slowly through the invisible forces that hold everything together, and sometimes tear it apart. From the dark energy that expands the universe, to the strange symmetry behind all physical laws. We'll explore the most fundamental layers of reality, gently, quietly, and with wonder. There's no rush here, just curiosity, calm, wide-eyed, and patient. Whether you are curled up in bed under quiet stars, or letting go of the day beneath soft indoor light, I'd love to know, where in the world are you listening from? And what time is it for you right now? If you're feeling safe, sleepy, or just a little more curious than usual, you're in exactly the right place. And if this kind of quiet exploration helps you rest, or helps you feel something, even just a little wonder, please consider liking the video, or tapping subscribe. It truly helps more sleepy minds find their way here. Now, take a deep breath. Feel the stillness settle in. And let's begin our quiet descent into the strange and beautiful edges of what we know, and the forces that may still be hiding in the dark. Dark energy, a force that pushes the universe apart. You wouldn't feel it on your skin, you wouldn't hear it in the silence, and even the most sensitive instruments can't capture it directly. Yet something, vast and invisible, is steadily, relentlessly tearing the universe apart from the inside, stretching the very fabric of reality, not with violence, but with quiet persistence, like a breath that never ends. This isn't an explosion, it's not a wind or a wave, it's something stranger, a pressure, a push, a repelling force built into the vacuum of space itself. We call it dark energy, and though we have no direct evidence of what it is, we are surrounded by its consequences. Galaxies are not only moving apart, they're accelerating away from one another. The further we look into space, the faster those galaxies recede. It defies gravity. It contradicts intuition, but it's happening. And the only way to explain this cosmic acceleration is to assume that the universe is permeated by something that exerts negative pressure. A kind of anti-gravity that doesn't pull objects together, but pushes them apart. This isn't just a tweak in the math. It redefines our understanding of what the universe is made of. Roughly 68% of the entire cosmos appears to be this dark energy. More than all the matter, all the stars, all the galaxies, all the dark matter combined. And yet we don't know what it is. It doesn't clump, it doesn't glow, it doesn't decay, it doesn't absorb or emit anything we can detect. It is not made of particles in the traditional sense, and it doesn't seem to fluctuate like quantum fields. It's just there, smooth, uniform, ever present. Its closest mathematical cousin is something Einstein once proposed, and later called his biggest blunder, the cosmological constant, a fixed energy density that exists even in a perfect vacuum. When modern astronomers discovered the accelerating expansion of the universe in the late 1990s, that blunder returned triumphantly as a leading explanation. But calling it a constant doesn't make it any more comprehensible. Why should empty space have energy at all? And if so, why that amount? Not more, not less, but precisely the value that would let the universe form galaxies, stars, life, and still drift apart over billions of years without tearing itself to shreds. Instantly. This is the dark energy puzzle. It's not just that we don't know what dark energy is. It's that the tiny value we observe seems absurdly, almost impossibly fine-tuned. The quantum vacuum, according to theoretical estimates, should have a density 10 to the power of 120 times larger than what we see. That's a 1 followed by 120 zeros. A mismatch so vast that it is considered the most glaring discrepancy between theory and observation in all of physics. And yet, here we are, living in a universe that expands ever faster, guided by this phantom force. What does it mean to live in a cosmos ruled by something so enigmatic. It means that space is not passive. It means that emptiness is not truly empty. Every cubic centimeter of space contains an energy that cannot be tapped, cannot be stopped, and cannot be ignored. It's as if the universe itself wants to be alone, as if every galaxy is being gently nudged toward cosmic solitude. This has profound implications for the fate of everything. If dark energy continues to dominate, the universe will not end in fire or collapse. It will end in coldness, in distance, in silence. Galaxies will fade beyond the cosmic horizon. Stars will burn out. Black holes will evaporate. And eventually, even atoms may decay, leaving nothing but a vast, thin fog of particles, drifting in ever-expanding emptiness. This scenario, known as the Big Freeze, is a direct result of dark energy's push. But some theories suggest stranger possibilities. If dark energy's strength increases over time, if it's not a true constant, but a dynamic field, then even bound systems like galaxies, solar systems, and atoms could eventually be torn apart in what's called the Big Rip. In that vision, everything from clusters of galaxies down to the molecules in your body would be unbound by this accelerating force, shredded not by violence, but by inevitability. The timeline varies, depending on the model, from tens of billions to hundreds of trillions of years. But the concept remains the same. Dark energy may not just shape the cosmos, it may end it. So where does that leave us now? Searching, theorizing, guessing. Some physicists propose quintessence, a new kind of dynamic field that changes over time, perhaps evolving through cosmic history. Others suspect dark energy could be a sign of something even deeper, that our theory of gravity breaks down at large scales. Modified gravity theories aim to explain cosmic acceleration without invoking a mysterious new substance. Still others look to extra dimensions, string theory, or the landscape of possible universes, where dark energy's value is just one realization among an infinity of other outcomes, most of which would not allow life. That's the anthropic view. We observe this specific value of dark energy, because if it were any different, we wouldn't be here to ask about it. But is that satisfying, or is it a stopgap? An elegant shrug in the face of mystery. Whatever dark energy is, it's not just a theoretical abstraction. It's the dominant component of our universe. It affects the past, the present, and the future. It dictates the large-scale structure of the cosmos. It may hold clues to the nature of space-time itself. It might even be entangled with other mysteries, like the origin of inflation, the fate of information in black holes, or the true quantum nature of the vacuum. And it raises philosophical questions as well. If the universe is accelerating, then there are regions of space we will never see, places where light will never reach us, no matter how long we wait. Every second, more of the universe slips beyond our reach. Cosmic isolation is not just a poetic metaphor. It is a measurable, inevitable fact. We live in an era of cosmic light, surrounded by stars, signals, beauty. But that era is temporary. In the far future, a lone civilization might look up at a dark, empty sky and see nothing but its own stars. No galaxies, no clues. Without knowing dark energy once pushed everything away, they might assume they were alone. So today, we ask, what is this force that hides behind every moment, every expansion, every silence between galaxies? And how can something so cold and invisible feel so intimate? Maybe it's because it forces us to reckon with scale, with loneliness, with impermanence. Maybe it's because in studying the force that pushes everything apart, we are reminded of the preciousness of what remains close. In this quiet universe, governed by a force we cannot see, we search not just for knowledge, but for connection, meaning, and the courage to face the infinite. The geometry of space-time, when curves become force. What if I told you that the force you feel pulling you to the ground is not a force at all, but a symptom of something far stranger? Something curved and invisible beneath your feet. You were taught that gravity keeps you from floating into the sky, that it holds the moon in orbit and shapes the movement of the planets. But that explanation simple as it sounds, hides a far deeper truth. Gravity is not a pull in the traditional sense. It is the bending of the very fabric of reality, and you are falling, not because something is tugging at you, but because you are following the curves of a four-dimensional geometry that dictates how matter moves. Space-time, the union of space and time into a single continuous fabric, is not a passive stage on which events unfold. It is an active player in the cosmic story, warping and rippling in response to mass and energy, and in turn, guiding those very things through its distortions. Imagine a trampoline with a heavy ball in the center. Smaller objects placed nearby will roll toward the depression, not because they are pulled, but because the surface is no longer flat. Now expand this metaphor into 4 dimensions, with time included as part of the stage, and you begin to approach what Albert Einstein unveiled in his general theory of relativity. Mass tells space-time how to curve, and curved space-time tells mass how to move. But this is not merely a poetic restatement of gravity. It is a radical reimagining of what force means, where geometry itself has the final say in how objects fall, orbit, collide, or drift endlessly through the void. You see, in Newton's world, gravity was an invisible rope that tied masses together, exerting instantaneous action at a distance. But in Einstein's universe, that rope vanishes, replaced by a graceful warping of the underlying coordinate system itself, so that what we interpret as acceleration is, in fact, the natural motion of bodies following the straightest possible paths in a curved reality called geodesics. You are not being pulled to Earth. You are moving in a straight line through a curved landscape. And what you call weight is simply your resistance to being deflected from that straight path by the solid ground beneath you. The implications are dizzying. If mass curves space-time, then every massive object is like a sculptor shaping the geometry around it. Stars, black holes, galaxies. Even you slightly distorting the cosmic weave with your presence. But unlike ordinary geometry, where lines and angles behave predictably on flat paper, the geometry of space-time is dynamic, shifting with energy and momentum, pulsing with gravitational waves that stretch and compress the very medium through which light and causality travel. And unlike any force you have ever encountered, gravity cannot be shielded, blocked, or reversed. It is built into the structure of existence, the architectural framework of reality itself. As your understanding deepens, something unsettling begins to surface. If space and time are interwoven, and if geometry dictates motion, then time itself must be malleable, bent, stretched, dilated by the presence of mass and the speed of motion. And this is not a thought experiment. It is reality. A clock on a mountaintop ticks faster than one at sea level because it experiences a slightly weaker gravitational curvature. Astronauts in orbit age just a bit slower than those on Earth due to both velocity and gravity's effects on space-time. Time is not a universal constant. It is local, personal, and variable, a byproduct of the path you take through the geometry of the universe. And so is space. The distance between 2 points can change depending on your trajectory and your frame of reference. These are not illusions. They are measurable, undeniable consequences of curved space-time. It means that your intuitive understanding of distance, time, simultaneity, and motion are all approximations, valid only under the calm, slow, and weak gravity conditions of your daily life. But in the extremes, near black holes, at the edges of the universe, in the milliseconds after the Big Bang, geometry behaves wildly. Curvature becomes intense, and the behavior of time and space warps into something almost unrecognizable. This is why light can orbit a black hole, why gravitational waves ripple out from cataclysmic collisions of neutron stars, and why the early universe was a turbulent ocean of expanding geometry, not an empty void waiting to be filled. You are living inside a four-dimensional sculpture that is constantly reshaping itself in response to everything it contains. The universe is not just expanding, it is stretching its own coordinate system, redefining its geometry in every direction, every moment, everywhere. But here is where things become even stranger. If space-time geometry can bend and ripple, then perhaps the geometry itself is the key to unlocking the deepest laws of nature. Geometry has long been the language of physics, from Euclid to Riemann, from Newton to Einstein. But now it has evolved into something more than a tool. It has become the arena in which fields interact, particles acquire mass, and the quantum world brushes against the cosmic. In quantum field theory, the vacuum is not empty, but buzzing with virtual particles, fields dancing in and out of existence. These fields are defined not just by energy, but by the geometry of the space they inhabit. A photon does not merely move. It follows the curvature of the geometry, experiencing space-time as a path, not a stage. And in more advanced theories like string theory or loop quantum gravity, space-time itself is not continuous, but granular, a quantum fabric woven from the smallest possible threads of geometry. In these models, geometry is not background, but foreground. It is the main character, the active agent, the code beneath the simulation. Gravity becomes an emergent property, not a force, but a statistical behavior of micro-geometric bits. The curvature we observe may arise from entanglements and information constraints in a deeper, pre-space-time realm. This means that when you fall to Earth, when the moon circles our planet, when galaxies form spirals, they are not obeying a command, but reacting to a script written in the invisible grammar of geometry, where lines are curves and time is a slope. And yet, despite its elegance, this geometric understanding reveals its own puzzles. Why is the universe so flat on large scales, as observed in the cosmic microwave background radiation? What selected this specific geometry among infinite possible configurations? Is there a deeper principle, a symmetry, a law that forced the cosmos into this peculiar shape? And if so, what happens when geometry itself fails, at singularities, at the edges of black holes, in the first instant of the universe's birth? General relativity, for all its beauty, breaks down at these extremes. The equations become singular, the curvatures infinite, the fabric torn. This hints that our geometric picture is incomplete, that a more fundamental theory must describe what geometry emerges from, not just how it behaves. It may be that space-time is not fundamental at all, but emergent from a deeper quantum reality where cause and effect dissolve, and where geometry is born from entanglement, information, or topological flows. Perhaps time itself is not a straight axis, but a swirl, a loop, a consequence of observers slicing the geometric loaf differently. Perhaps mass is not an inherent property, but a distortion, like a dent in a mattress caused by your hand, that tells fields how to bend, and bending tells energy how to behave. And what does this mean for you, standing on the surface of a spinning planet, feeling the tug you call gravity? It means you are not being pulled. You are falling through a curved existence, with your trajectory shaped not by invisible strings, but by invisible slopes. It means you live in a universe where time is not a river, but a hill, where space is not a void, but a tensioned fabric, where movement is not chosen, but written into the bends of your reality. And it means that to truly understand gravity, you must let go of the idea of force altogether, and embrace the revelation that the universe moves, not because it is pushed, but because it is shaped. Geometry becomes fate, curvature becomes cause, and every step you take is a journey along a path etched into the silent, stretching, wrinkling, whispering geometry of space-time. You are not just in the universe. You are written into its curves. You are shaped by its angles. You are held by its bends. And in that realization lies something both deeply humbling and transcendent, that the universe does not control you with chains, but with contours, and your entire existence is a graceful glide along the invisible geometry of everything. Dark matter's gravitational grip, felt but never seen. You move through a world built on visible things, solid walls, shining stars, dense planets. But what if I told you that everything you can see, every atom you've ever touched, is merely a glowing film stretched across an invisible skeleton of gravity you cannot detect? There's something massive, something immense, silently surrounding you, holding galaxies in its grasp, sculpting the universe's shape, dictating the orbits of stars and galaxies alike. Yet it neither emits nor reflects light. It cannot be photographed, painted, or pierced. It is the unseen majority, the missing matter, the invisible hand behind the architecture of the cosmos. We call it dark matter, but in truth, we don't know if it's even matter. In the way we usually understand it, we only know it's there because of how it pulls. Its fingerprints are everywhere, but never in the form of light, never in the form of shadow, only in the curves and tugs of gravitational distortion. In the 1930s, astronomer Fritz Zwicky noticed something peculiar. Galaxies inside the Coma cluster were moving too fast to be held together by the visible matter alone. If gravity operated only through the stars and gas they contained, these galaxies should have flown apart, and yet they stayed. Zwicky proposed the existence of Dunkel Materie dark matter, a hidden mass anchoring the cluster together. At the time, the idea was bold, even fringe. But over the decades, similar anomalies surfaced. Spiral galaxies spin in a way that defies expectations. If only visible matter provided the mass, the stars at the edges should orbit more slowly than those near the center. Yet they don't. Instead, the outer stars whirl at nearly the same speed as those inside, as if an invisible halo of mass is keeping them tethered. This flat rotation curve is now one of the clearest signs that something unseen surrounds every galaxy, forming a kind of gravitational cocoon. Observations of gravitational lensing, where light from distant galaxies bends around invisible masses, further confirm this presence. It's like watching the shape of a ghost by how it warps the light behind it. And the Bullet Cluster, a collision of galaxy clusters observed in 2006, delivered perhaps the most dramatic evidence. The normal matter from the colliding clusters was slowed and heated, visible in X-rays, while the mass, traced through gravitational lensing, had passed through undisturbed. This showed that the bulk of the mass, the dark matter, interacted gravitationally, but not through friction or heat. It moved like a shadow immune to fire. And yet, for all this evidence, we still don't know what dark matter is. It doesn't fit within the standard model of particle physics. It could be made of undiscovered particles, perhaps weakly interacting massive particles, axions, sterile neutrinos, or something stranger still. It might not be particles at all. It might be a modification to our understanding of gravity, a sign that our theory of how mass bends space-time breaks down at large cosmic scales. Physicists are building elaborate underground detectors in quiet mines and mountains to try to capture a rare interaction, a flicker, a recoil, a whisper of a dark matter particle colliding with normal atoms. So far, they've found nothing. Every silence deepens the mystery. Some hypothesize that dark matter could form structures of its own: dark galaxies, dark stars, even dark planets, ghostly mirrors of our visible world, floating beside it, but forever unreachable. Others wonder if dark matter existed before the Big Bang, as a relic of a previous universe, or if it interacts through forces we cannot yet name, and still, its gravitational grip never falters. Simulations of galaxy formation without dark matter fail. Without its presence, the early universe would not have clumped fast enough to form the structures we see today. It's the scaffolding of galaxies, the unseen spine of cosmic architecture. Without it, we would not be here. Yet dark matter doesn't clump like normal matter. It doesn't collapse into stars. It doesn't form planets. It lingers like a diffuse halo around galaxies, spreading farther than the eye can see. It may pass through you every second, billions of dark matter particles, sliding silently through your skin, your bones, the earth, without leaving a trace. You are not solid to it. You are almost transparent. That realization alone bends the mind, that your body could be bathed in a sea of matter and never feel it. The Earth moves through the galactic dark matter halo as it orbits the Sun, creating an invisible wind of particles rushing past us. Detectors try to pick up this wind by waiting for tiny changes in signal throughout the year, like a wind vane searching for a breeze that doesn't blow. Nothing. Not yet. Meanwhile, astronomers continue mapping the dark matter distribution across the sky by studying how light bends around invisible shapes. These cosmic cartographers build maps of an unseen empire, tracing its borders by distortions in space. The results suggest that galaxies live in vast filaments of dark matter, forming a cosmic web, like threads of silk stretched across billions of light years, with galaxies as glowing dew suspended at their nodes. This web is the true structure of the universe, not defined by light, but by gravity. We are merely the luminous dust that gathers along its bones, and in that understanding lies something humbling, that the visible universe, with all its stars and galaxies, makes up less than 5% of what's out there. The rest is dark matter and dark energy, both invisible, both mysterious, both essential. Everything we've ever seen is a minority detail. We are the exception, not the rule. Some believe that cracking the secret of dark matter could unravel the next great revolution in physics, like discovering atoms, or quantum mechanics, or relativity. Others think it will take entirely new instruments, or even new ways of thinking. What if we're blind not just to dark matter, but to the very questions we should be asking? What if our entire framework is a reflection of light-based bias, and reality is built on shadows? Dark matter forces us to ask whether visibility should be the standard for existence. Just because something is unseen doesn't mean it's unimportant. Sometimes it means it's everything. Maybe dark matter is not hiding. Maybe we are simply not yet wise enough to see. Maybe the silence isn't an absence, but a different kind of presence. One that listens rather than speaks. One that holds rather than shines. And maybe, just maybe, the universe has always been held in the arms of something that never needed to be seen to be real. Quantum vacuum fluctuations. Energy from supposed emptiness. You've been taught to think of nothingness as absence, a still, empty silence, with no sound, no substance, no story. But in the world of quantum physics, that assumption collapses almost instantly, revealing a startling truth. The vacuum isn't empty at all. It boils. It shivers. It seethes with a restless energy that never ceases. A kind of jittery pulse embedded in the very fabric of space-time itself. Even in the quietest region of the cosmos, far beyond the reach of stars, where temperature approaches absolute zero and no particles seem to drift, space is not truly still. Instead, it flickers with activity, a chaos of creation and annihilation, where pairs of virtual particles pop into existence and disappear in trillionths of a second, like whispers you almost heard, or dreams you almost remembered. This is the strange and wondrous phenomenon, known as quantum vacuum fluctuations. And it's not science fiction, it's one of the most experimentally supported realities of modern physics. At first glance, the idea seems nonsensical. How can nothing contain energy? But that very question arises from the limits of our everyday intuition, not from the true nature of physical law. In classical physics, a vacuum is simply the absence of particles. But in quantum field theory, the language of our most accurate physical models, every point in space is described by quantum fields that are always present, always vibrating, even in their lowest possible energy state. These fields cannot be entirely silenced. Even when you remove all real particles, cool everything to near zero, and shield the region from external influence, these fields still possess what's called zero-point energy, an irreducible jitter baked into the system by the uncertainty principle. According to Heisenberg's uncertainty principle, you cannot precisely know both the energy and the time of a system. So even the vacuum must have fluctuations in energy, however brief. These fleeting ripples give rise to virtual particles, temporary disturbances in the field that momentarily act like particles, with mass and momentum, only to vanish before violating conservation laws. And though they're not directly observable in the way electrons or photons are, Their effects are, they influence real-world processes in ways we can measure, from the subtle shifts in an atom's energy levels to the vast-scale evolution of the early universe. These ghostly flickers aren't theoretical abstractions. They shape reality. The Casimir Effect is a hauntingly beautiful demonstration of this truth. Place two metal plates extremely close together in a vacuum, and they will be pulled toward each other. Not because of any force between them, but because the quantum vacuum between them contains fewer modes of fluctuation than the surrounding space, creating a pressure imbalance that pushes the plates together. No particles, no heat, no magnetism. Just the whisper of quantum nothingness exerting a force. We've measured this. We've built instruments sensitive enough to detect that the vacuum isn't passive. It acts, it pushes. It has a personality, and if that sounds small, scale, and niche, consider this. Many cosmologists now believe that quantum vacuum fluctuations were the seeds of all structure in the universe. In the earliest moments after the Big Bang, during a period known as cosmic inflation, the universe expanded faster than the speed of light, stretching tiny quantum ripples in the vacuum into vast cosmic perturbations that would later become galaxies, stars, and planets. Everything you see when you look at the night sky, the great sweeping arms of spiral galaxies, the quiet glow of distant quasars, the very atoms in your body, may have started as mere flickers in a quantum field, amplified by expansion into structure and matter. So, in a deeply literal sense, you are not born of stardust alone. You are also born of vacuum fluctuations, the echoes of an emptiness that was never truly empty. And the more you study this concept, the more it forces you to question the boundary between something and nothing. Because in quantum physics, nothingness is never truly still. Even a state with the lowest possible energy is teeming with probabilistic potential, like a perfectly calm pond that hides invisible currents. This baseline unrest is a consequence of the most fundamental rules of nature. And yet, it raises uncomfortable questions. If vacuum fluctuations have energy, and space is filled with them everywhere, why doesn't that energy overwhelm everything? In fact, when physicists try to calculate the energy density of the vacuum based on known quantum field theories, they get an answer that's wildly off, by as much as 120 orders of magnitude, compared to what we observe as the actual energy driving the expansion of the universe, known as dark energy. This staggering mismatch is one of the greatest unresolved mysteries in theoretical physics, and goes by the name of the cosmological constant problem. It's a paradox. Quantum theory says the vacuum should have far more energy than what we observe, but something, somehow, is suppressing it. Or perhaps our understanding of the vacuum is incomplete. Either way, it tells us that the vacuum is not a finished idea. It's a question still being asked by the universe. And this brings us to the philosophical edge of the topic. If even nothing is something, then what do we mean when we say something exists? If particles can emerge from fluctuations in the vacuum, then what separates existence from potentiality? Could our whole universe have emerged from a quantum fluctuation? Some cosmologists seriously consider this possibility, that in the void of some larger metaspace, a kind of multiversal foam, a fluctuation large enough occurred that it gave rise to a self-sustaining bubble of space-time. Our cosmos, no matter. No energy input, just a quantum blip large enough to inflate, cool, and evolve into the stars, planets, and living beings we now observe. And, if this sounds implausible, remember that quantum tunneling allows particles to appear on the other side of energy barriers they shouldn't be able to cross. Reality at this scale is not deterministic. It's statistical, probabilistic, and astonishingly permissive. Which means the boundary between imagination and manifestation might be thinner than we're comfortable admitting. But don't let this unsettle you. Let it expand you, because it means that potential is everywhere. Even in silence, even in stillness, even in the places you thought were void. The vacuum isn't nothing. It's a hidden symphony of possibility, humming with a music too fast and subtle for your ears, too deep and brief for your eyes, but they're nonetheless. And the more we study it, the more it teaches us that the foundations of existence are not made of blocks or boundaries, but of waves, of flickers, of allowed uncertainties that somehow add up to solid walls, warm light, and the breath in your chest. So the next time you sit alone in a quiet room, don't mistake the silence for absence. Under your skin, in the spaces between atoms, in the vast dark between galaxies, the vacuum is dancing. You were born of it. You are shaped by it. You are never not surrounded by the invisible energy of becoming. And perhaps the most extraordinary lesson of quantum vacuum fluctuations is this: even where there is nothing, the universe finds a way to express its presence. Even in stillness, there is motion. Even in emptiness, there is creation. And if the cosmos itself can rise from a fluctuation in the void, what might be waiting to rise from the silence within you? Virtual particles, fleeting ghosts that shape reality. You've probably never noticed them, but your entire life is surrounded, penetrated, by apparitions that appear from nothing, exist for less than a heartbeat of time, and vanish without a trace, leaving behind consequences more real than stone. These are not ghosts in the poetic sense, nor the spiritual residue of some distant myth, but the mathematically predicted, experimentally verified flickers of energy we call virtual particles, the ephemeral phantoms of the quantum world, that emerge not from matter but from possibility itself. They're not particles in the way we normally imagine, tiny, discrete building blocks flying through space, but transient disruptions of underlying fields, fleeting wrinkles in the fabric of reality that obey no classical rules. And yet, without them, atoms wouldn't hold together, forces wouldn't act, and even the most stable objects would fall apart. In quantum field theory, the deepest language we've yet found to describe how nature works, every particle is a vibration in a field that fills all of space. And these fields are never perfectly still. Even in what we call empty space, they fluctuate, jitter, and momentarily give rise to these ghost-like entities, particles that are borrowed from the energy of the vacuum, permitted to exist briefly by the strange generosity of Heisenberg's uncertainty principle, which allows nature to trade precision in energy for brevity in time. These virtual particles exist on credit, a kind of quantum loan that must be repaid almost instantly, and for this reason, they can't be directly observed. But their fingerprints are everywhere. They mediate the fundamental forces, influence the properties of real particles, and have consequences that have been measured in some of the most precise experiments in the history of science. One of the clearest demonstrations of their reality is the Lamb shift, an observed deviation in the energy levels of hydrogen atoms, caused by the electron's constant interaction with a cloud of virtual particles flickering in and out around it. Another is the anomalous magnetic moment of the electron, whose behavior diverges ever so slightly from classical predictions due to the quantum sea of virtual photons surrounding it. And perhaps the most famous is Hawking radiation, the theoretical process by which black holes may slowly evaporate over time, as pairs of virtual particles are torn apart at the event horizon, one falling in, the other escaping to become real. In each case, the effect is real, the math is precise, the energy is measurable, and yet the source is invisible, untouchable, forever forbidden from direct detection. So what are we to make of these ghosts? Are they illusions, tricks of the math, or are they evidence that reality itself is built on things that never quite existed in the way we expect? Unlike real particles, virtual particles don't obey the mass energy relations that define E equals mc squared. They don't follow clean trajectories through space-time. They are internal lines in Feynman diagrams, the scribbled bridges between incoming and outgoing states in particle interactions. You don't see them in the detectors, but you couldn't explain the outcome without them. They're the middle act of a play whose beginning and end you can measure, but whose center is hidden in suggestion, and that middle act is where everything important happens. Virtual particles are the messengers of forces. When two electrons repel each other, it's not because they sense one another across space. but because they're constantly tossing virtual photons back and forth, like invisible notes between strangers who will never meet. The strong force, which binds quarks into protons and neutrons, is mediated by virtual gluons, whose self-interactions create a dense storm of confinement inside hadrons. Even gravity, in speculative extensions of quantum theory, would be mediated by virtual gravitons, massless, spin-2 ghosts we've yet to detect, but which may one day complete the puzzle of quantum gravity. And here lies the paradox. Virtual particles aren't real, but they are essential. They don't exist in the sense that they can be caught or counted, but they shape every measurable event in the quantum world. It's like trying to describe a river without mentioning the current. You can see the banks, the fish, the ripples, but the movement, the very life of the river, comes from something you can't grab. In this sense, virtual particles challenge our most basic ideas about what it means to exist. Do you need to persist in time to be real? Do you need to be observed, or is influence enough? These questions are not abstract. They touch the heart of what science can describe and what it merely gestures toward. And the deeper we look, the more it seems that influence without presence is a defining feature of our universe. Even the structure of empty space is shaped by these fleeting entities. In the Casimir Effect, for instance, we observe two metal plates placed a few nanometers apart in a vacuum being pushed together, not by any classical force, but by the pressure of virtual particles excluded between the plates. The vacuum isn't passive, it acts. It has preferences, it pushes. And virtual particles are the reason. They even ripple through cosmology. Some interpretations of the cosmological constant, the mysterious energy causing the universe's expansion to accelerate, point to vacuum energy as the culprit, an energy born of quantum fluctuations and the ceaseless appearance of virtual particles on cosmic scales. And yet, when we try to calculate the energy of the vacuum using quantum field theory, we arrive at a value so enormous, over 10 to the power of 120 times too large, that it reveals a deep and unresolved disconnect between theory and observation. This is the vacuum catastrophe, one of the greatest unsolved problems in physics. And at its heart are virtual particles, silent, ubiquitous, misunderstood. They also lead us to question the very structure of cause and effect. In quantum tunneling, for example, particles pass through barriers they shouldn't be able to surmount. Another phenomenon, enabled by the temporary distortion of energy conditions allowed by virtual contributions. It is as if the laws of nature are written in pencil at small scales, not in ink, and virtual particles are the authors of those edits. So what does it mean that reality is shaped by things that never fully exist? That the forces that govern the universe depend on interactions between particles that emerge only to vanish? Never observed, never fixed, never caught. It means that reality is more fluid than we thought, that cause can arise from almost being, from near presence, that the universe is not just made of things, but of the spaces between things, of the dance, not just the dancers. And perhaps there's something deeply human in that. We, too, are shaped by what's never seen, emotions never spoken, memories barely recalled, choices not made but imagined, influence without permanence, shadows that guide us. And so, the next time you think of reality as solid, as made only of what you can measure or hold, remember the virtual particles, the fleeting ghosts that sculpt the world you live in. They aren't illusions. They are the soft breath behind every force, the heartbeat behind every atom. And they remind us that sometimes the most powerful presences are the ones that never stay. The strong nuclear force, stronger than anything you felt. Strength as we usually understand it is a matter of scale. How much you can lift, how much pressure something can withstand, how forcefully one thing pushes against another. But there exists a force so staggeringly powerful, so immeasurably intense, that it defies every human reference point for what strong even means. And yet it operates entirely out of sight, deep within the atomic nucleus, governing the hidden architecture of matter itself. This is the strong nuclear force, often simply called the strong force. And despite being the mightiest of the four fundamental forces in nature, it remains the least visible to our everyday experience. Not because it's rare, but because it's profoundly localized, restricted to scales so tiny that the entirety of its action unfolds within a space smaller than a millionth of a billionth of a meter, at that microscopic frontier, where protons and neutrons reside tightly packed inside atomic nuclei. The strong force takes over, binding these particles together against immense odds. Because they should repel each other. Protons, all positively charged, should fly apart due to electromagnetic repulsion. And yet they don't. They hold. They cling. They fuse into nuclei that endure for billions of years, all thanks to a force 100 times stronger than electromagnetism, 10 to the power of 6 times stronger than the weak nuclear force, and 10 to the power of 30, 8 times stronger than gravity. But unlike gravity, which has an infinite range and weakens with distance, the strong force behaves in the opposite way. It is short-ranged, confined within the nucleus, but overwhelming in its domain. This paradox of intense power confined to invisible boundaries is one of the many ways the strong force challenges intuition. It doesn't just glue the nucleus together, it makes the very concept of matter possible. Without it, atoms wouldn't exist. Chemistry wouldn't exist. Stars wouldn't ignite. Life would be unthinkable. And yet, despite its central role, the strong force is anything but simple. Its behavior is governed by the complex mathematics of quantum chromodynamics, where quarks interact by exchanging particles called gluons, messengers of the strong interaction. But this is no ordinary exchange. Gluons themselves carry the color charge that defines the strong force, and they can interact with one another, creating an endlessly dynamic and self-modifying field inside hadrons like protons and neutrons. This interaction creates what physicists call confinement, the principle that quarks and gluons can never be isolated. Try to pull two quarks apart, and the energy between them grows rather than weakens, like stretching a rubber band that never snaps, eventually creating a new quark, anti-quark pair, instead of allowing freedom. It's a force that doesn't just resist separation, it forbids it. In this sense, the strong force is the ultimate enforcer of cohesion, not only within particles, but within the laws that define particles themselves. It is not a force that allows independence. It demands relationship, and that requirement gives rise to something astonishing: the very mass of protons and neutrons. The particles that make up atomic nuclei is not primarily from the quarks inside them, but from the energy of their interaction. Einstein's equation, E=mc², tells us energy and mass are equivalent. And here, in the strong forces domain, that truth is brought to life. More than 95% of your body's mass comes not from the mass of your particles, but from the energetic dance of confinement and motion governed by the strong force. You are made not just of matter, but of energy held in place by an invisible storm, and this storm cannot be calmed or viewed directly. To understand it, physicists turn to lattice quantum chromodynamics, a computational approach where spacetime is represented as a grid, and the complex field equations are solved step by supercomputers, revealing the internal pressure, binding energy, and fluctuations that define the strong interaction. These simulations have matched experimental data with breathtaking precision, confirming that the strong force isn't a theoretical abstraction. It's the underlying scaffold of physical existence, but it's also responsible for something far more dramatic: the energy released in nuclear fusion. When two light atomic nuclei merge, as in the heart of the Sun, a small portion of their mass is converted into energy due to the strong force reshaping the internal structure. This process powers every star in the night sky and is also the basis for hydrogen bombs. The unleashed fury of fusion tamed only by magnetic fields or stellar gravity, that radiant warmth you feel on your skin from the sun. It's the gentle echo of the strong force, that golden glow at sunset, the light that grew the plants that feed you, the photons that bounced off your surroundings to show you the world. They're all traces of quarks, rearranged under the rules of the strong interaction. Yet, for all its power, the strong force respects distance. Beyond the size of a nucleus, it simply vanishes. This makes it the most aggressive, but also the most localized of all forces, a paradox of dominance and discretion. It doesn't radiate like electromagnetism. It doesn't tug at planets like gravity. It's not responsible for decay like the weak force. Instead, it defines identity. A proton is a proton, not just because of its quarks, but because of the way the strong force holds them. It's a sculptor of stability, not just a binder. And in this way, it sets the stage for all complexity. Without it, the periodic table wouldn't exist. There'd be no stable elements, no compounds, no cells, no structures. And yet, the strong force also hints at danger, because when nuclei are split, as in nuclear fission, the reconfiguration of the strong force releases vast amounts of energy. Nuclear reactors, atomic bombs, the radiological remnants of war, all harness the shift in binding energy of the strong force. That something so invisible can be so decisive, so quiet, and yet so catastrophic, is perhaps the strongest testament to its reach. And still, there are questions. Why does the strong force exhibit such precise behavior? Why are its effects so tightly confined? Could there be variations, new particles or interactions beyond the standard model, that subtly modify its role at extreme energies or scales? In particle physics, the strong force is the domain of deep, inelastic scattering, of hadron colliders, of asymptotic freedom, where at ultra-high energies, quarks seem to move more freely because the strong force weakens. Yes, unlike all other forces, the strong interaction behaves in reverse. It gets weaker at higher energies and stronger at lower ones. This counterintuitive behavior is what allows physicists to model early universe conditions and probe the birth of matter itself. When quarks and gluons formed a quark-gluon plasma, a state recreated briefly in heavy ion collisions at CERN and Brookhaven, where the strong force, for a fleeting moment, becomes a fluid field of unbound energy. And so we find that the strong force is not merely a binder, but a historian. It remembers the earliest moments of the universe and inscribes them into every atom. It's the guardian of integrity and the architect of release. And the next time you hold anything solid in your hand, a stone, a cup, your own heartbeat, remember that beneath that calm surface rages a storm that never ends. A field of tension so strong it cannot be undone, a force so fierce that it makes the existence of matter not just possible, but inevitable. The strong force is not a push, it is not a pull, it is a declaration. This shall hold. And in that holding, the universe begins. Color charge and quantum chromodynamics. Why quarks stay trapped. Sometimes the most powerful forces in the universe are not the ones that push or pull, but the ones that never let go. And deep within every proton and neutron lies a confinement so absolute, so relentless, that no known energy in the cosmos can break it. Here, at the core of matter, live the quarks, fundamental particles held eternally captive by the strongest known interaction in nature, the strong nuclear force. But this force doesn't work like gravity or electromagnetism. It doesn't fade with distance. It grows stronger the farther it stretches, like a rubber band that tightens the more you pull. And the color that defines this interaction is not the red, green, or blue of visible light, but a symbolic charge in the language of quantum mechanics, a mathematical label that governs how quarks interact according to the rules of quantum chromodynamics, the theory describing the strong force in subatomic physics. Unlike electromagnetism, where opposites attract and forces diminish with separation, quantum chromodynamics obeys its own strange logic. Quarks can't exist in isolation. Nature forbids it. They must always combine in color-neutral groups, like trios in protons and neutrons or quark, antiquark pairs in fleeting particles called mesons. The further apart you try to pull quarks, the more intense their bond becomes. And when that bond is stretched to the breaking point, it doesn't break by releasing a quark. It breaks by summoning new quarks into existence from the quantum vacuum, creating new pairs that instantly lock themselves into confinement. In this way, the strong force writes its own unbreakable script. No quark shall ever be alone. This behavior, called confinement, is one of the most stunning features of the strong nuclear force. But its true nature lies even deeper. To understand why quarks remain forever bound, you must enter the realm of gauge theory, a mathematical framework where quantum chromodynamics arises from the symmetry group known as SU3, which governs the color charge of quarks. Within this system, the force carriers, the gluons, are not like the neutral photons of electromagnetism. Gluons carry color charge themselves, meaning they not only transmit the force, but also interact with one another in an intricate web of self-coupling, feedback, and endless complexity. The result is a field that doesn't fade or smooth out with distance, but one that twists and tangles into chaotic knots, forming structures far beyond the reach of our direct senses. The vacuum in this theory isn't empty at all. It is teeming with invisible energy, virtual particles, and strange topological structures, like instantons and flux tubes, that shape how quarks behave. These are not abstract possibilities. They are physical features of the universe, embedded in the very essence of matter. They explain why the mass of a proton is not simply the sum of the masses of its three constituent quarks. In fact, the majority of that mass arises from the dynamic motion and interaction of quarks and gluons, the kinetic and potential energy locked within the quantum storm of the strong force. We know this not just from theory, but from practice. Computational frameworks like lattice quantum chromodynamics allow scientists to simulate these phenomena by breaking spacetime into a discrete grid and observing how quarks and gluons behave. And in high-energy particle collisions, like those performed at CERN, we've never seen a free quark escape. Even when we smash protons together at nearly light speed, what emerges are new bound states, new hadrons, because the strong force instantly traps any would-be free quark in a fresh cage of interaction. It is as if nature has a built-in fail-safe. Whenever you try to violate its symmetry, it doesn't punish you. It remakes the world around you to maintain the rules. And here's where things become even more strange. While forces like gravity and electromagnetism weaken as you separate objects, the strong nuclear force grows stronger, a behavior known as infrared slavery. But when quarks are extremely close together, they behave almost as if they are free. This seemingly paradoxical condition is called asymptotic freedom, and it means that quarks within protons and neutrons dart around with relative independence until you try to pry them apart. Then the force leaps into dominance, an unyielding tether that won't be severed. This realization earned a Nobel Prize in Physics in 2004 and redefined how we understand interactions at the smallest scales. And yet, even with all this mathematical clarity, we still cannot truly visualize what's happening. We can simulate the numbers, describe the symmetries, and predict the outcomes, but we cannot see the threads of the strong force, nor the vibrant tapestry of color charge weaving through the vacuum. What we understand are the consequences: no free quarks, no decay into isolated pieces, and no exceptions. It's like a secret language spoken beneath the surface of all matter, a song we know exists only by watching the way particles dance. And so you begin to see the universe differently. You understand that the protons making up your body are not quiet, permanent things, but dynamic storms of interaction. Within them, gluons fire endlessly between quarks, virtual particles flash in and out of existence, and energy churns in an ever-renewing confinement. The atom is not a marble, it is a thundercloud. And this confinement isn't a flaw, it's the law. The reason quarks never escape isn't because they are weak, but because they are too tightly bound by a force too perfect, too fierce, and too elegant to permit solitude. In that strange truth lies a deeper metaphor. The most fundamental parts of matter are not allowed to be alone. And maybe neither are we. Maybe there is something in the architecture of existence that demands connection, that binds the smallest parts of reality not through freedom, but through unity. The strong nuclear force doesn't release its quarks. It creates new bonds in response to every rupture. It does not break, it transforms. And perhaps in some quiet, unspoken way, that is what keeps us whole too. Electroweak unification, two forces, one origin. There's a hidden simplicity buried within the chaos of nature, an elegant truth that reveals itself only when we look beyond what's obvious. And one of the most profound of these revelations is that what we once thought were two distinct forces, electricity and the weak nuclear force, are actually two expressions of a single underlying phenomenon, a unity known as electroweak unification to the naked eye. And even to early science, the electromagnetic force and the weak force seemed entirely unrelated. One governs the attraction between charged particles, gives rise to light and magnetism, powers motors, and fuels stars through photons. The other, the weak force, governs radioactive decay, transforms particles into others, and enables the sun's fusion through the change of quarks. One is long-ranged and familiar, the other is short-ranged and subtle. But under the surface of reality, when temperatures soar to the unimaginable scales that existed in the earliest instants after the Big Bang, trillions of degrees in mere billionths of a second, these two forces become indistinguishable. They merge into a single entity described by the electroweak theory, a groundbreaking unification first proposed in the 1960s by Sheldon Glashow, Abdus Salam, and Steven Weinberg, whose combined insight earned the Nobel Prize and reshaped our understanding of the universe's fundamental architecture. In this high-energy domain, the distinctions between electromagnetic and weak interactions dissolve, and what remains is one cohesive force, mediated not by separate rules, but by a unified mathematical framework. This isn't just theoretical poetry, it's experimentally confirmed. The discovery of the W and Z bosons in 1983 at CERN provided the clearest physical validation of electroweak theory. These particles, heavy cousins of the photon, are the messengers of the weak force and gain their mass through interactions with the Higgs field, a mechanism that also explains why the unified electroweak force splits into two distinct behaviors as the universe cools. It's as if, when the cosmic temperature drops below a critical threshold, the symmetry of the universe fractures, and a single elegant force becomes two different ones, each carrying its own role, its own messenger, its own domain. This process, known as spontaneous symmetry breaking, is the quiet fracture that created difference where there was once unity. And at the center of this breaking is the Higgs mechanism, a field permeating all space, which interacts with particles to give them mass, and which treats the photon and the W and Z bosons differently. That's why the photon remains massless and mediates a long-range force, while the W and Z become massive and act only over extremely short distances. But originally, they were all part of the same electroweak family. Twins born of the same principle, diverging only after the universe cooled enough to impose constraints on how that symmetry could manifest. In many ways, electroweak unification is a window into how nature simplifies at high energy. The closer we get to the origin of time, the more distinctions blur. What looks complicated at low energies becomes unified at higher scales. This insight lies at the heart of particle physics' greatest ambition: the search for a grand unified theory, a deeper framework in which the electroweak force and the strong nuclear force would themselves merge. And perhaps, if we go even deeper, connect with gravity in a theory of everything. Electroweak theory is our first solid step down that road. It's a blueprint for how forces that appear separate can emerge from a common source, how symmetry and its breaking define what's possible, and how the universe's earliest moments still echo through the behavior of particles today. And the more you examine this unification, the more it teaches you to doubt the divisions we assume are natural. Are forces really different? Or are they just different manifestations of a deeper whole? What we call electromagnetism and the weak force are simply two low-temperature behaviors of a higher truth. And it forces us to reconsider the nature of duality, not as opposition, but as divergence from unity, as consequence of cooling. This is not just a lesson in physics. It's a lens for thinking about everything from biology to consciousness. At high energies, complexity simplifies. Differences collapse into symmetry. Distinction becomes expression. And from that point of view, everything we see, light, charge, decay, mass, is a kind of unfolding, not of chaos, but of broken symmetry. It's tempting to think of unification as something abstract, something that matters only to theorists. But Electroweak unification has real consequences. It explains why radioactive decay happens the way it does. It predicts the precise mass and behavior of W and Z bosons, which have been measured with incredible precision. It gives us a framework to understand neutrinos, those ghost-like particles that barely interact with matter, but are abundant across the cosmos. And it shapes the behavior of the early universe, where Electroweak processes set the stage for the first elements to form, for matter to separate from antimatter, for the seeds of galaxies to arise. And this unity also tells us something about the structure of matter, that even the forces that seem to tear particles apart are connected to the forces that create coherence. Electromagnetism gives us light, chemistry, magnetism. The weak force gives us decay, transformation, radiation, but both spring from a deeper symmetry, a unified equation that under high energy makes no such distinction. This is not unlike how hot iron becomes paramagnetic, losing its directionality, only to form magnetic domains as it cools. The order emerges from a phase change. Symmetry gives way to structure, and structure gives rise to what we call complexity. But underneath, the equation hasn't changed. Only the conditions have. And so, when we ask whether nature is inherently diverse or inherently unified, the answer is both. But unity comes first. Diversity is what happens when unity cools. And perhaps, hidden in that cooling, is the story of why our universe feels both structured and dynamic, both stable and capable of change. Electroweak unification is more than a technical achievement. It's a philosophical invitation to reconsider how we draw lines. The universe did not start with 4 forces. It started with fewer, and those fractured as the universe aged. What we experience now are differentiated behaviors, sculpted by cooling, shaped by broken symmetry, and carried forward by fields that still whisper the unity they once held. So the next time you flip a light switch or hear the word radiation, remember that these aren't separate domains. They are distant cousins from the same ancestral force, divided only by the cooling of time. And the next time you wonder whether difference means disconnection, look closer. The Electroweak force says otherwise. It says that deep under the surface of contrast lies coherence. It says that what's broken was once whole, and may be again under the right conditions. And perhaps that's the most beautiful message physics can offer, that even separation can contain the memory of unity, and that sometimes understanding what holds the world together means looking beyond the names we've given things, and asking instead, where did they begin? Gravitons, the hypothetical particles of gravity. What if the entire universe, with its spiraling galaxies and expanding edges, was being tugged, twisted, and held together by something we've never seen? Not a force field, not a curvature of space, but a particle so elusive that it may not even exist in the traditional sense, yet so essential that without it, nothing would orbit, nothing would fall, nothing would form. We call this hypothetical entity the graviton, a quantum messenger of gravity, the last missing piece in the puzzle of unifying all forces under a single theory. For every other fundamental interaction, electromagnetic, strong, weak, There exists a known or well-theorized force carrier, a boson that mediates action between particles. But gravity, our most familiar force, the one that grounds us, that sculpts the cosmos, that bends light and time itself, has no confirmed quantum agent. That is, unless gravitons are real. Their proposed role is deceptively simple: to transmit the gravitational influence from one mass to another, just as photons carry light. But beneath that simplicity lies one of the most challenging and profound mysteries of modern physics. Because gravity, unlike other forces, is woven into the very geometry of space-time. According to Einstein's general relativity, mass doesn't just exert force, it reshapes the fabric of reality. So if gravity is curvature, if it's the bulging of the cosmos in response to energy, then what does a graviton mean? It would imply that even this smooth, continuous warping is made of discrete quanta, teeny, indivisible chunks of gravitational influence, zipping back and forth between masses at the speed of light, stitching space together. But herein lies the conflict. General relativity is classical and continuous. Quantum theory is probabilistic and discrete. Uniting them has defied every attempt. Gravitons are the theoretical bridge between these two, seemingly incompatible realms. If they exist, they would be massless, like photons, yet they would have spin too, which means they don't behave like any of the force carriers we've confirmed so far. And detecting them, nearly impossible with current technology. Their interactions would be so weak that they'd pass through planets, stars, even black holes without a whisper. A single graviton might fly through the entire universe without ever touching anything. So why do physicists search for them? Because gravitons are not just a solution, they're a necessity in many frameworks trying to explain how everything works at the smallest scales. In string theory, for example, the graviton naturally emerges as a vibration mode of a closed string, elegantly implying that gravity too has a quantum origin. In loop quantum gravity, another contender, spacetime itself is quantized, and gravitons may be viewed not as particles in space, but as excitations of space. These aren't just academic distinctions, they hint at fundamentally different realities, where what we call space is not a void but a dynamic, discrete structure. Imagine gravity not as a pull, but as the result of quantum chatter between masses, mediated by the silent passing of gravitons that never rest, never decay, never get absorbed. It's a beautiful image, this invisible, massless whisper that glues the stars together and sculpts the path of every falling apple. And yet, there's a deeper reason we care. Without a quantum theory of gravity, our understanding of black holes, of the Big Bang, of the universe's most extreme conditions remains incomplete. Hawking radiation, for instance, arises when quantum effects touch the curved horizon of a black hole. But what really happens inside? Does information survive? Can time reverse? These questions are unanswerable unless gravity, like everything else, has quantum rules. Gravitons might hold the key. But how do you catch something that won't interact? Theoretical proposals have ranged from detecting subtle echoes in gravitational wave patterns to analyzing quantum noise in highly controlled laboratory systems. But so far, all we have are indirect clues. Whispers in the math, hints in the structure of the universe, philosophical necessity rather than physical evidence. Still, the implications are staggering. If gravitons exist, then even the void is not silent. Every atom in your body, every motion you make, would be broadcasting gravitational messages. Infinitesimal signals emitted by your mass, dancing across the universe at light speed, never stopping, never fading. You are, in a sense, always gravitationally seen by everything else. And you, in return, feel the sum total of all other masses, down to the tiniest flicker of a graviton. That's a vision of connectedness that goes far beyond metaphor. It suggests a universe where gravity isn't just curvature or geometry, but a conversation held in the language of quantum particles. And like all good conversations, it leaves traces, ripples, structure. Even cosmic inflation, the exponential expansion of the early universe, might have imprinted gravitational fluctuations so subtle that they trace the birth of gravitons themselves. These traces could still be etched in the polarization patterns of the cosmic microwave background, waiting for us to decode them. To find a graviton would be to pierce the veil between the known and the unknowable. It would mean we can truly understand spacetime, not just as a backdrop, but as a dynamic participant in the quantum game. And if that's true, then perhaps we could even manipulate gravity, shape it, shield it, or bend it in ways that today seem like science fiction. Anti-gravity, wormholes, warp drives. These ideas, long banished to the realm of fantasy, would become at least mathematically plausible. And all because of a particle we cannot see, cannot touch, and may never detect directly. So the graviton becomes a symbol of humility in science, of curiosity that refuses to yield, of unity waiting to be discovered. It's a reminder that the most powerful truths may not be the loudest ones. They may not announce themselves with flashes or bangs. They might float, undisturbed, at the edge of our theories, waiting for us to look closely enough, to listen deeply enough, to believe that even gravity has a quantum heartbeat. And that heartbeat may sound like a single, weightless particle dancing in the dark. The force carriers, bosons that mediate reality. They don't make headlines like black holes or steal attention like quantum entanglement. But the bosons, those subtle, silent particles, are the threads holding reality together, weaving invisible laws into the fabric of the universe, without asking for credit, recognition, or applause. And without them, nothing would hold, nothing would move, nothing would become. Not because they are solid or mighty, but precisely because they are not, because they mediate rather than dominate, because they serve not as bricks in the wall but as the mortar between them, the messengers of every interaction and the unseen hands that negotiate every fundamental relationship in nature. Relationships so foundational that without them, matter itself would fall apart into silence, into irrelevance, into a universe with no meaning, no cohesion, no becoming. The word force can be misleading, conjuring images of pushing and pulling, of muscular strength or sudden motion. But in physics, a force is not a thing that acts. It is a relationship, a permission, a rule for how something may affect something else. And bosons are the carriers of that rule, the literal translators of interaction, ensuring that when two particles meet, they understand what is allowed, what is possible, and what must occur. Bosons don't build the particles of matter like quarks and leptons do, but they choreograph how those particles interact, how they stay together or fall apart, how they remain stable or decay, and even whether they acknowledge one another at all. Among the most familiar of these carriers is the photon, the quantum of the electromagnetic field, which not only gives us visible light, but is responsible for every electromagnetic interaction in the universe. The way electrons stay bound to atomic nuclei, the way magnets attract or repel, the way wireless signals pass through the air, all of it governed by a storm of virtual photons. You can't see and can't isolate, but which flicker between charges like telegrams sent between dancers in an ancient routine, telling each participant when to pull, when to push, when to sway in concert with the field. But not all bosons travel so freely. Others are bound within more intimate and intense dances, like gluons, the carriers of the strong nuclear force, that flit constantly between quarks inside protons and neutrons, locking them in with a grip so tight that no single quark has ever been found alone. Not because they don't exist independently, but because the gluon's influence grows stronger the more you try to pull them apart, like a cosmic rubber band, whose tension doesn't weaken with distance, but amplifies, until it snaps, not by letting go, but by generating new quarks from the energy of separation itself, an act of creation born out of resistance. a paradox that makes confinement the very signature of strength. These gluons don't merely mediate force, they participate in it, since unlike photons, they carry the very color charge that they act upon, creating a loop of self-interaction so recursive, so complex, that it forms a vibrant sea of energy within every nucleon, a dance so rapid and tangled it resists clear visualization and defies simplicity, but not significance, for it is this perpetual internal motion that gives protons most of their mass, not the mass of the quarks themselves. And in this way, the gluons act not only as communicators, but as architects of substance itself. Other bosons, too, have been proposed not merely as facilitators of what we know, but as gateways into what we don't. The graviton, a hypothetical quantum particle of gravity, is one such ghost, a thing never seen, never confirmed, yet so elegant in its theoretical necessity that physicists can't quite stop invoking it, imagining it as the vibration within spacetime that would carry gravitational influence in a quantum world, a world where space is not continuous, but granular, not smooth but pixelated, and where gravity is not curvature, but quanta, where mass speaks and space-time listens in ripples, in waves, in the hush of gravitons passing through everything without friction, without slowing, without detection, yet still bending the path of every planet, still shaping the arcs of galaxies, still keeping the moon bound to the Earth not by tether or tension but by the soft persuasion of curved emptiness. But this vision is still incomplete, because while the Standard Model elegantly describes the bosons of three fundamental forces, electromagnetism, the strong force, and the weak, it omits gravity entirely, as if the stage of existence were set, but one of its most commanding voices remained off, script, unrehearsed, whispered only in theories not yet confirmed, in math too ambitious for current machines to test, leaving us with a map of reality whose borders dissolve into speculation the moment we try to unify the celestial with the quantum. And even within the Standard Model, there are whispers of others, particles that do not fit, particles that may still exist just beyond our detector's reach, like the axion, another hypothetical boson that might solve the mystery of why certain symmetries in quantum chromodynamics don't break the way we expect. A whisper so soft, it could explain the unseen half of the universe. A particle so aloof, it might travel through entire planets without ever touching anything, yet collectively account for the dark matter that outweighs all visible stars, that anchors galaxies in gravitational nets we can't explain, that haunts every rotation curve and every lensing arc with its stubborn refusal to shine. These bosons, if they exist, would belong to forces we have yet to name, forces not experienced by ordinary matter, but which might govern a parallel sector of the universe, a shadow realm of interactions that mirror ours in form, but diverge in content, creating a kind of hidden physics that intersects ours, only gravitationally, only through the pull of presence, not the exchange of light. This raises an unsettling but thrilling possibility that what we perceive as the universe may be only a subset of all there is, that our bosons, our force carriers, mediate only the theater we are equipped to observe, while other acts unfold on stages hidden behind the curtain of invisibility, with their own rules, their own actors, their own bosons delivering their own messages in languages we do not speak, cannot translate, cannot even hear. And yet, even within the limits of what we do know, the bosons we've confirmed already tell us that reality is not built of things alone, but of relationships, that substance matters less than structure, that energy matters less than interaction, that the universe is less a collection of objects and more a living web of permissions. Each particle given its script by the presence of a boson, each motion enabled by an exchange, each force not a push but a handshake, not a command but an agreement, not a domination but a dialogue. Bosons do not insist, they suggest. They connect, they convey. They are the language of how things relate, and in that sense, they are the poetry of physics, invisible verses that rhyme between the building blocks of everything. enforcing not rigidity but rhythm, not laws but structure, not control but coherence. And perhaps this is the truest lesson they offer. Not in how they act, but in what they allow, in the way they make complexity possible without imposing it, in the way they let particles be themselves, while still making them part of a whole. They show us that power is not always in possessing, but in permitting, that the deepest forces are not the ones that impose their will, but the ones that create the space for others to act. Without bosons, particles are islands. With them, the universe becomes an archipelago of connection, a cosmos not of solitude but of structure. And in this structure, we find not just physics, but philosophy. We find a reflection of the very nature of communication, of cooperation, of presence, not in the shouting of one, but in the listening of many. Bosons remind us that to move anything, to change anything, to make anything happen, there must first be a link, a willingness, an exchange. They do not occupy, they mediate. They do not shout, they echo, and through that echo reality resounds. The Casimir effect, when nothing creates pressure. You wouldn't expect two objects placed in a perfect vacuum. No air, no light, no heat, no particles at all, to move toward each other as if pulled by some hidden hand. And yet that's exactly what happens in one of the strangest verified phenomena in quantum physics, the Casimir effect, where nothing quite literally pushes. Imagine placing two uncharged, parallel metal plates just a few nanometers apart in an environment stripped of every visible force, every known interference. And still, they begin to drift together, drawn not by magnetism, not by gravity, but by the invisible fluctuations of the quantum vacuum itself. This isn't science fiction, nor is it some unrepeatable curiosity. It's been measured, calculated, observed in lab after lab, and it defies every classical expectation of how objects should behave when left completely alone. What the Casimir effect reveals is not just that the vacuum isn't empty, but that its emptiness is structured, selective, and capable of exerting measurable force. The explanation begins with quantum field theory, where every point in space, even empty space, is described by fields that never truly rest. These fields, like the electromagnetic field, have vibrational modes, and these modes, waves of possibility, not particles, exist even in the absence of any actual energy input. They are the natural ground hum of the universe, a baseline unease that no amount of cooling, shielding, or isolation can fully remove. Now, place two plates very close together in this restless sea, and something remarkable occurs. The space between them restricts the wavelengths of these fluctuations, just as a violin string can only resonate at certain frequencies, depending on its length. The narrow gap between the plates only allows certain quantum fluctuations to exist between them. Shorter wavelengths fit, longer ones don't. But outside the plates, in the wider universe, all wavelengths are allowed. This creates an imbalance, more quantum pressure from the outside, less from the inside. The result, a net inward force. The plates are pushed together by the vacuum itself, or more precisely, by the absence of longer wavelengths between them. What feels like attraction is actually exclusion. What appears to be motion toward is really pressure from beyond. This is the Casimir effect. It's the vacuum saying, I'm not nothing. I am alive with influence. And that alone should make us pause. Because we often assume that power comes from substance, from mass, charge, interaction. But here is a force that emerges from constraint, from subtraction, from a boundary imposed on emptiness. It suggests that the universe isn't just made of things, but of limits, and that even what we cannot see or touch can shape the behavior of what we can. The implications are profound. At the nanoscale, the Casimir force becomes strong enough to affect real-world engineering. In microelectromechanical systems, which are used in everything from phone sensors to medical implants, designers must account for Casimir attraction to avoid parts sticking together. The vacuum, it turns out, is an active participant in technology, but more than that, the Casimir effect hints at something deeply unsettling and deeply beautiful. That space is not a passive backdrop, but a player in the cosmic drama. And the more we explore its subtleties, the more we are forced to rethink our assumptions about how the universe works. For instance, this force emerges not from anything that's real, in the classical sense. No fields crossing space, no particles moving between the plates, but from potential, from possibilities that are suppressed, from quantum modes that are denied entry. It's not the presence of energy, but the absence of allowed fluctuations that generates the force, that turns our expectations inside out. In classical physics, force comes from something mass times acceleration, field lines, direct interaction. In quantum physics, force can come from not something, from the difference between what could happen and what is allowed to happen, from the shadow cast by invisible rules. The Casimir effect is a whisper of this difference, and it's measurable. The first experimental verification came in 1997, using a sphere and a flat plate to approximate the parallel geometry. The force matched predictions almost exactly. Since then, precision measurements have confirmed the effect over and over again, tightening our understanding of how quantum fields behave under boundary conditions. But even now, it raises thorny questions. Could the same vacuum energy that causes the Casimir force also be responsible for dark energy, the mysterious force accelerating the expansion of the universe? Both arise from vacuum fluctuations. Both are omnipresent, subtle, and enormously consequential, yet their measured magnitudes differ by orders of magnitude, a gap we still don't understand. This is known as the cosmological constant problem, one of the most perplexing mysteries in physics. And the Casimir effect sits quietly at its heart, not as a cause, but as a clue. It's a controlled glimpse into the unpredictable nature of vacuum energy, a way to poke the surface of something we don't yet know how to see. It tells us that the vacuum isn't neutral. It's political. It reacts differently depending on context. It cares about shape, about geometry, about what is and isn't allowed. And in doing so, it teaches us that reality isn't merely built from particles or energy, but from constraints, permissions, and the ghostly consequences of denied possibilities. And isn't that also a kind of poetry? That force can arise from limitation, that absence can press, that emptiness can bend matter. It's like discovering that silence can sing, or that stillness can push. The Casimir effect is not a relic of high-energy theory. It's a living demonstration of how delicate the universe really is, how even the calmest space is filled with tension, how proximity itself can summon power from nothing, and it invites us to reflect more deeply on what we think of as nothing. Because if the vacuum can generate pressure, what else might be hiding in the gaps of what we overlook? What else are we missing by focusing only on what is there? The Casimir effect invites us to consider a universe where every boundary matters, where distance is not neutral, where even nothing contains difference. And in that light, you begin to wonder how many other forces in your life, your body, your relationships, arise not from what's present, but from what's constrained. How many pressures are caused by invisible limits? How many outcomes are shaped not by action, but by exclusion? What seems still may not be, what seems silent may be humming. What seems empty may, in truth, be pressing in on you from all directions. So the next time you think you're alone in a quiet space, pause. Somewhere in the quantum soup that underlies every moment, every molecule, the vacuum is watching your boundaries. Not intrusively, but naturally. Mathematically, constantly, and even though you cannot feel it directly, the Casimir effect reminds you that even in the absolute absence of everything, the universe still speaks. It whispers in pressure, it curves in silence, and sometimes it even pushes you forward. Quantum field fluctuations. When fields come alive on their own, there is something eerily beautiful about a still surface, suddenly rippling with motion. like a calm lake stirred by an unseen wind, or a silk curtain that shivers without touch. And in the subatomic theater of quantum reality, this eerie stirring happens not to things, but to the very fabric from which things emerge, to the fields that underlie existence itself, fields that should, in theory, lie dormant in the absence of energy or stimulation, and yet, paradoxically, they tremble with activity, even in the coldest, emptiest voids, as if the universe refuses to sit still, as if reality cannot bear silence, as if nature's default state is not calmness, but restlessness. These are quantum field fluctuations, brief, spontaneous bursts of energy that arise in what we mistakenly call nothing. A word that in physics conceals one of the richest, most dynamic, most surprising aspects of nature. To understand this, you must let go of the classical notion of particles as tiny billiard balls bouncing in a vacuum, and instead envision a universe made not of particles alone, but of invisible fields stretching through all space. Fields for electromagnetism, for the strong force, for each type of particle, and even for gravity itself, continuous, ever present fields that fill the cosmos even in the absence of matter, even where space seems dark, silent, and abandoned. In quantum field theory, every particle is simply a quantized excitation of its corresponding field, much like a vibration along a string produces a musical note, and just as strings can be plucked accidentally by random disturbances, quantum fields, too, can experience momentary spikes in energy without any external input. Spikes that generate fleeting, ghost-like particles that exist for mere instants, violating the classical conservation laws just long enough to stay within the bounds of Heisenberg's uncertainty principle, which allows energy and time to play a trade-off game. The shorter the time interval, the more uncertain the energy can be. These transient disturbances, these virtual particles, aren't directly observable in isolation, but their fingerprints are unmistakable, leaving measurable effects in physical systems, shifting the energy levels of electrons in atoms, contributing to the strength of interactions, even subtly nudging particles in otherwise symmetrical settings. And what's most startling is that they emerge not from heat, not from collisions, but from the vacuum itself, suggesting that the vacuum isn't truly empty, but teeming with potential, humming with fluctuations, like a sleeping dragon that stirs in its slumber, shaping the world even as it dreams. One of the most astonishing demonstrations of this comes from the Casimir Effect, where two uncharged metal plates, placed incredibly close together in a vacuum, are mysteriously pulled toward each other, not by electromagnetic attraction or gravity, but by the absence of vacuum energy between them compared to the outside, a pressure difference born of nothing, created by the quantum fields themselves choosing, for reasons woven into the math of reality, to fluctuate more freely outside than in, like sound waves, silenced in a narrow alley while roaring in open air. This pressure of nothing reveals that the vacuum isn't empty. It has structure, it has behavior, it has measurable consequences. And if a vacuum can create pressure, can influence objects, can shift energies, then perhaps it is more accurate to think of the vacuum not as a void, but as a medium, a subtle, restless ocean whose surface always trembles, even when it appears calm. And just as wind patterns shape waves, and tides move the ocean's depths, quantum fluctuations might shape the very structure of space-time, might drive the birth of particles, or even spark the origin of the universe itself. For many cosmological theories suggest that the Big Bang didn't erupt from a pre-existing something, but rather from a quantum fluctuation in an unstable vacuum, an accident of energy that inflated into everything, a blip that became a bang that became a cosmos, implying that the spark of creation itself may have been born from the jitter of fields that couldn't sit still. But this isn't just a poetic metaphor. It is embedded in the very calculations of modern physics, in the predictions of quantum electrodynamics, in the corrections of quantum chromodynamics, In the strange renormalization procedures required to account for infinite self-interactions, and in the non-trivial vacuum states that define the ground energy of quantum fields. These fluctuations are not noise, they are structure. They influence how particles interact, how forces behave, how energy is distributed across space. And in experiments involving high-precision measurements, such as the anomalous magnetic moment of the muon or the Lamb shift in hydrogen atoms, the fingerprints of vacuum fluctuations are not theoretical curiosities, but vital components of real-world outcomes, measurable and consistent, predicted and confirmed to extraordinary precision. And yet, for all this rigor, there remains an aura of mystery. Why do these fluctuations exist at all? Why doesn't the universe choose a truly quiet vacuum? A flat, still field with no stirrings? Why is there this irreducible, irrepressible dance beneath the stillness? A quantum restlessness that persists no matter how cold or empty a region becomes. The answers, if they exist, may lie beyond the current limits of our equations, in the structure of spacetime itself, or perhaps in hidden symmetries not yet broken, or even in deeper principles, yet undiscovered. Perhaps the universe cannot tolerate a perfect zero. Perhaps stillness is unstable. Perhaps existence itself emerges from the refusal to be nothing. Some physicists propose that the so-called zero-point energy of these fluctuations contributes to the cosmological constant, the mysterious driver of the universe's accelerated expansion. And if this is true, then the jitter of fields in empty space is not a minor background effect, but a major actor in the destiny of the cosmos. A quiet force stretching galaxies apart, steering the arc of time itself. Others suggest that these fluctuations might interact with fields or dimensions we cannot yet observe, shaping a deeper substrate of reality, or forming the template upon which all observable phenomena rest. And through all of this runs a provocative idea that what we call particles, and even forces, are secondary to the fields themselves, that reality is not made of things, but of the trembling in the fields beneath things, and that the truest measure of existence is not solidity or permanence, but fluctuation. It is not the stone, but the shimmer, not the pillar, but the pulse. And if this is so, then perhaps we, too, are expressions of fluctuation, temporary emergences in a field that cannot rest, transient peaks in a sea of quantum becoming. We think of ourselves as stable, as continuous, as consistent, but under the hood of biology lies chemistry, and under chemistry lies physics, and under physics lies fields that ripple, even when left alone, even when told to sleep, even when pressed into the void. And so we must ask, if the background of reality is never still, if even nothing is alive with change, what does it mean to be? Is identity a crest in the sea of fluctuation? Is thought itself a resonance in the trembling field? Is the mind a byproduct of vacuum restlessness? In a universe where silence is never truly silent, where emptiness births pressure, where stillness breeds movement, where existence itself is a fluctuation, then perhaps the deepest truth is not that things are, but that things happen. And in that happening, in that pulse, that shimmer, that fluctuation, we find the origin of all things, not in permanence, but in becoming, not in being, but in the refusal to stay still. Gluons, the invisible threads holding quarks together. Not everything that holds the universe together can be seen. And sometimes the most fundamental forces don't push or pull, like gravity or magnetism. They stitch. Deep within every proton, inside every neutron, beyond the limits of even the most powerful microscope, lies a frantic, blazing storm of particles that should fly apart, but don't. This stability isn't a given. It's earned. It's enforced by one of nature's most overlooked but essential agents, the gluon. While photons carry light, and W and Z bosons handle radioactive change, gluons are the silent enforcers of unity, the invisible threads that bind quarks together so tightly that they've never been observed alone. The name gluon comes from glue, and it's not just poetic. it's exact. Gluons are the mediators of the strong nuclear force, which is not only the strongest of the four fundamental forces, but so disproportionately powerful that it can overcome the mutual repulsion of positively charged quarks, hold them together inside particles smaller than a millionth of a billionth of a meter, and still have enough leftover intensity to bind entire atomic nuclei. But this force doesn't behave like others. It grows stronger with distance. A bizarre reversal of every other force we know. The more you try to pull quarks apart, the tighter the gluons bind them. It's as if the universe has drawn a line and said, these cannot be separated, no matter how hard you try. This is a property known as confinement, and it means quarks and gluons are forever locked inside hadrons, particles like protons and neutrons, doomed to an eternal quantum prison that only ends when they transform, but never when they separate. The deeper you look, the more intense this force becomes, until pulling two quarks apart requires so much energy that instead of escaping, they create new pairs, new matter, to stay confined. And so we've never seen a free quark, never isolated a gluon. We know them only by their footprints. Jets of particles in particle accelerators, the mass they create through binding energy, the impossibility of tearing hadrons apart without spawning more. Gluons themselves are massless, but unlike photons, which glide through the universe without interacting with each other, gluons carry the very charge they influence, something called color charge in the framework of quantum chromodynamics. This means gluons interact not just with quarks, but with other gluons, weaving a web of mutual enforcement that turns the interiors of protons and neutrons into writhing, dynamic maelstroms. The word color here doesn't mean what it does in everyday life. It's a label physicists use to track how quarks interact under the strong force. There are three types: red, green, and blue, and their opposites. For a particle to exist stably, its color charges must add up to white, just as primary colors blend into neutrality. Gluons mediate this complex balancing act, constantly being exchanged between quarks, changing their colors, maintaining the harmony that holds matter together. But they don't do this calmly. The interior of a proton is not a serene place. It's a roiling sea of virtual particles, of quark-antiquark pairs that blink into and out of existence, of gluons whizzing in every direction, exchanging color and momentum in a chaos that's more like weather than geometry. And yet, from this storm emerges something astonishingly stable. Your body, the Earth, the stars, are built from particles whose internal components are anything but still. It's like constructing a cathedral out of bees in flight. This dynamic dance is governed by equations so complex that they can't be solved directly. We use supercomputers to simulate them in a field known as lattice QCD, where space is broken into a grid, and the interactions of gluons and quarks are calculated step by step, a computational feat that reveals the masses of hadrons, not from their components' weight, since quarks themselves are surprisingly light, but from the kinetic and potential energy of the interaction itself. In fact, most of the mass of a proton comes not from the mass of its quarks, but from the energy of the gluon fields, holding them together. This means that most of the mass of everything you know, your body, your breath, the rock beneath your feet, comes not from particles, but from invisible tension, from the quantum choreography of gluons. It's a humbling realization that substance is the product of confinement, and that solidity comes from ceaseless motion. But gluons also teach us something even stranger, that not all forces get weaker with distance. In gravity and electromagnetism, distance brings relief. The farther two objects drift, the less influence they have on each other. But the strong force, mediated by gluons, rebels against this. It rises as you stretch it, like a rubber band that refuses to snap. It's this very behavior that gives rise to confinement, and this reversal of expectation leads to an unexpected duality, that strength and restriction are sometimes the same. That what binds most tightly may do so by resisting freedom more as pressure increases. And in this, the gluon becomes a metaphor as much as a particle. one that whispers of unseen bonds, of forces that grow more powerful the more they are tested. But gluons are not only theoretical curiosities. We've seen their indirect effects in high-energy particle collisions, where quarks momentarily taste separation before the strong force yanks them back into being. Not through retreat, but by transforming energy into more matter. This phenomenon, called hadronization, is what produces particle jets in collider experiments. You start with a quark, antiquark pair, or a gluon, and end with a spray of stable particles, like pions and kaons, all because the strong force refuses to let anything walk away alone. It's like an algorithm that rewards tension with multiplication. You try to break it, and it gives you more of itself. This behavior leads to a strange kind of creative destruction in trying to probe the gluon's nature. We only generate more particles, more complexity, more noise, and this makes the gluon both elusive and omnipresent, a ghost that fills the room by hiding in plain sight. It's also why we speak of the gluon seas inside protons, a dense jungle of interactions that is never still, never simple, never clear. The deeper we peer, the more we realize we're looking not at structure, but at process. And if this leaves you feeling dizzy, uncertain of what's real, that's part of the point. The gluon reveals a layer of reality built not from things, but from relationships. Quarks do not exist as individuals. They are defined by how they interact. Their properties, mass, spin, color, only make sense in the context of their bonds. The gluon enforces that relationality. It is not a brick, but a thread, not a particle, but a promise. And from that promise, all of matter arises. So the next time you hold something in your hand, remember, it holds together not because of surface tension or structural integrity, but because of countless interactions occurring inside each atom, each nucleus, each proton. Interactions ruled by gluons, invisible and unstoppable, stitching the world together from the inside out. You've never seen a gluon, but you are held by them. You've never touched one, but every moment you stand upright, every word you speak with vocal cords, made of cells, made of atoms, made of protons. That is gluon work, invisible work, threaded work, a work of holding that makes all becoming possible. The role of symmetry in physics, nature's hidden blueprint. There is a strange kind of order that hides behind the apparent chaos of the cosmos. A quiet rhythm not of time, but of structure, not of repetition, but of invariance beneath change. And though we may walk through life believing that the universe is messy, unpredictable, or arbitrarily stitched together, physics whispers a different truth. That everything we see, every force we feel, every particle that flickers into being, or vanishes into silence, dances according to ancient invisible symmetries. Not the decorative kind found in snowflakes or butterflies, but deep mathematical symmetries. Rules that say, if you do this, and nothing changes, then the universe agrees with you. This is the silent logic of invariance, and it underpins the most powerful theories in all of physics. Rotate the world slightly and it looks the same. That's rotational symmetry. Shift everything forward in time, and the laws still apply. That's time translation symmetry. These are not aesthetic preferences of nature, but hardwired rules that generate real consequences. Like conservation laws, the fact that energy is never created or destroyed arises, because the laws of physics don't change over time. Linear momentum is conserved, because space behaves the same no matter where you stand. Angular momentum persists because turning around doesn't affect the rules. These aren't coincidences. They are dictated by Noether's theorem, one of the most beautiful and profound connections in modern physics, which says that every continuous symmetry in nature gives rise to a conserved quantity. This means symmetry isn't just elegance. It's power, it's law, it's the reason anything behaves reliably at all. And as we dive deeper, symmetry doesn't just explain the behavior of systems. It shapes their very form. Why are there 3 dimensions of space? Why do particles fall into certain families? Why do forces behave differently at different scales? Behind every answer lies a symmetry, sometimes visible, often hidden, always consequential. Gauge symmetries, for example, determine how fundamental forces arise. In quantum field theory, insisting that the laws of physics remain unchanged when we make certain local transformations leads directly to the existence of interaction fields. It's not that we added forces into the model, it's that symmetry demanded them. Electromagnetism exists because the wave function of particles can be rotated in phase without changing observable predictions. That freedom, that symmetry, forces the introduction of the photon. The strong force comes from the more complex symmetry group SU3, governing the color charge of quarks. Each layer of physical interaction is born from a demand for invariance. Even the structure of the Standard Model, the most accurate description of matter and forces we possess, is not a collection of guesses, but a carefully balanced interplay of symmetry groups, ESU 3 times, ES, U2 times, U1. This isn't decoration. It's the very grammar of the universe. And yet, what makes this even more astonishing is that nature sometimes breaks its own symmetries. A mirror world, where left becomes right, might seem identical, but weak, nuclear interactions violate mirror symmetry, preferring one-handedness over the other. CP violation, where particles and antiparticles do not behave identically under mirror and charge flips, is one of the great mysteries of modern physics, and may be the reason matter dominates over antimatter in our universe. Symmetry breaking isn't a flaw, it's a mechanism. In the early universe, all forces may have been unified in a high symmetry state, indistinct and seamless. But as the cosmos cooled, those symmetries fractured like ice crystals forming in supercooled water, leading to the separation of forces, the appearance of mass, the structure of atoms, and eventually stars, galaxies, and minds. This spontaneous symmetry breaking is not destruction, it's birth. The Higgs field, for example, achieves its role precisely because the universe chose one configuration over others, breaking its symmetrical potential and endowing particles with mass. The field could have stayed balanced at the top of a metaphorical hill, symmetric in all directions, but it didn't. It fell, and in falling, it chose a direction, introducing asymmetry, and with it, reality as we know it. This interplay between symmetry and its breaking isn't just a mechanism, it's a pattern that repeats across scales. In crystals, symmetry dictates the arrangement of atoms. In biology, broken symmetries determine how an embryo develops a left and right side. In art and music, symmetry creates balance, while asymmetry introduces interest. Nature uses both, the rule and the exception, the frame and the crack, to build everything we know. But perhaps the most profound implication is that our deepest theories, the ones that reach toward quantum gravity, string theory, or grand unification, are ultimately attempts to discover higher symmetries, more inclusive invariances that explain why the lower ones work. Supersymmetry, for instance, posits a symmetry between fermions and bosons, matter and force particles, though we have yet to observe its consequences. String theory relies on intricate symmetry structures, like dualities and higher dimensional invariances, to stitch together quantum mechanics and gravity. The search for a theory of everything may be, at its core, a search for the ultimate symmetry, a pattern so fundamental that all others unfold from it. But what if symmetry isn't just a feature of physical law, but of reality's very architecture? What if the preference for balance, mirroring, and invariance is not only how the universe behaves, but why it exists in a coherent, intelligible form at all? Perhaps without symmetry, there would be no patterns, no equations, no conservation laws, no predictability, only chaos. Or perhaps the opposite is true, that symmetry is always there, even in the chaos, waiting to be uncovered, reframed, understood. As we build particle accelerators to higher energies, hoping to reveal new symmetries broken in the early moments of time, or map the cosmic microwave background for traces of primordial balance, we're not just doing physics, we're listening for the blueprint of reality, A blueprint that doesn't reside in one place, but echoes everywhere, like a melody played across space and time. Sometimes harmonious, sometimes dissonant, always meaningful. In the end, symmetry in physics is not just about shapes or equations. It's about the logic behind the laws, the consistency behind the phenomena, the deep whisper that says, even in a universe as vast and strange as ours, there are truths that hold still, even as everything else moves. The Higgs field, why anything has mass at all. You've probably never felt it, never touched it, never seen it shimmer or hum. And yet everything you know, everything that has weight or form or presence, owes its very existence to an invisible ocean that permeates the cosmos. The Higgs field. It's not a place you can point to, not a substance you can bottle or contain, but more like a background note, playing in every atom, a silent influence woven into the fabric of reality itself. Without it, there would be no chairs to sit in, no stars to ignite, no particles to gather and form the world. The Higgs field is the hidden sculptor behind mass, and its presence is so fundamental, so quietly persistent, that you don't realize the depth of its mystery until you imagine a universe without it. A place where light-speed particles flash endlessly without ever slowing, touching or clumping together. A place where you could never exist. But the Higgs doesn't just give things mass, it decides who participates in the architecture of matter, who drifts like a ghost, and who stands firm like stone. It does so, not by force, but by resistance. Particles moving through the Higgs field feel drag, a sort of cosmic molasses that tugs back just enough to give them weight. The more strongly they interact with the field, the heavier they become. It's not unlike wading through water. The deeper you go, the harder it is to move. But unlike water, the Higgs field is everywhere, always on, and incredibly selective. Some particles glide through barely touched. Others are gripped tightly and slowed, made dense and anchored. And this subtle process, the way particles couple with the Higgs, is what we interpret as mass. The photon bearer of light ignores the Higgs completely and remains weightless, which is why light races across the cosmos unchecked. The W and Z bosons, carriers of the weak force, interact intensely, and they're incredibly heavy. So heavy, in fact, that their mass is what limits the reach of weak interactions, letting them work only at the subatomic scale. This wasn't always the case. In the earliest instance after the Big Bang, before the Higgs field turned on, all these particles were massless, skimming across a high-energy field of symmetry, interchangeable and indistinct. Then, as the universe cooled, the symmetry broke. The Higgs field settled into a new ground state, an energetic shift, like a ball rolling into a valley, and in doing so, it transformed the rules of interaction. This phase transition wasn't a quiet change. It reshaped the laws of physics in an instant, locking in the mass of fundamental particles and forever altering the texture of the universe. And yet, it left no scar, no rupture, only the memory of its choice embedded in the way particles behave. Think about that. The difference between something and nothing, between you and emptiness, might hinge on a field choosing a resting state billions of years ago. But how do we know it's real? For decades, the Higgs was a ghost in our equations, mathematically necessary but physically unconfirmed. Then, in 2012, after decades of design, failure, collision, and hope, scientists at CERN announced they had found it. Not the field itself, but its quantum fingerprint, the Higgs boson. A ripple in the Higgs field, like a splash in an invisible ocean. The boson decays almost instantly, but tells us the field exists. Because without the field, there would be no ripple. This was more than a discovery. It was a confirmation that our reality is not built solely from matter or energy, but from fields, textures, and interactions that determine the very shape of existence. But the Higgs doesn't just answer questions, it raises them. Why does it couple more strongly to some particles than others? Why does it exist at all? Is it fundamental, or a shadow of something deeper? Some physicists believe the Higgs field might be part of a larger mechanism, perhaps one tied to supersymmetry, or extra dimensions, or the origin of dark matter. Others wonder whether the Higgs potential, the shape of its energy valley, is stable over cosmic time, or whether, somewhere far in the future, a quantum fluctuation might kick it into a deeper minimum, rewriting the laws of physics and collapsing reality as we know it. This is not science fiction, it's baked into our equations. The same field that makes existence possible might also contain the seeds of its undoing. And yet, even with that terrifying beauty, the Higgs remains humble, uniform, unchanging, ever present. It doesn't shout, it doesn't twist or churn, it simply is, a silent judge beneath all things, offering mass to those who ask, and remaining still to those who pass through. And in that stillness, it reveals a truth most of us overlook, that what defines substance is not how much of something exists, but how it interacts with what surrounds it. In a way, the Higgs field teaches us that identity is relational. A particle is not heavy or light on its own. It is made so by the way it moves through a hidden web of influence. And maybe we're the same. Maybe our own weight, our psychological mass, our sense of presence, comes not from some fixed core, but from how we interact with the fields around us. People, memories, meanings. Maybe your sense of being grounded is not internal, but contextual, just like particles gain mass by moving through the Higgs. Perhaps we gain substance by moving through others, through love, through pain, through understanding. So the next time you feel the weight of your body pressing into a chair, the gravity pulling at your limbs, remember that you are not heavy by accident. You are heavy because the universe allows you to be, because a silent field has given you permission to slow down, to gather, to stay, and in a cosmos filled with rushing light and restless particles, that gift, the gift of being able to rest, is more profound than we often realize. The Higgs field didn't have to be there, but it is. And because of that, so are you. Vacuum polarization, when nothing becomes electrified. What if the emptiest space you could imagine, utterly devoid of particles, fields, and matter, wasn't empty at all, but hiding an electric secret, so strange it could bend light, shift charges, and subtly alter the way forces behave, not through objects or collisions, but through the restless flicker of virtual particles born from pure potential. Welcome to vacuum polarization, one of the most unintuitive but essential features of quantum electrodynamics, where what we call nothing becomes momentarily electrified by the buzzing presence of ephemeral particle, antiparticle pairs, conjured from the uncertainty of space itself. In classical physics, a vacuum is a neutral, inert backdrop, a stage on which particles move. But in the quantum world, the vacuum is alive with fluctuations, and these fluctuations, when disturbed by the presence of a real electric charge, behave like an invisible swarm of responders. They reorganize themselves, aligning opposite charges in response to the disturbance, creating an effective screening effect that subtly alters how the original charge appears to observers at a distance. This is not fiction, it is a measurable, testable shift in the very constants of nature. Vacuum polarization doesn't merely describe a background phenomenon, it changes how we understand the electric field, revealing that every particle drags behind it a cloud of virtual responses, a quantum entourage that warps the vacuum's neutrality and shapes the fundamental strength of electromagnetism itself. To see how this happens, picture a lone electron placed into a vacuum. According to classical intuition, its electric field should radiate outward smoothly in all directions, diminishing with distance in a predictable, spherically symmetric way. But quantum theory tells a different story. The presence of the electron disturbs the vacuum, prompting it to respond, with virtual particle, antiparticle pairs, most commonly electrons and positrons, that briefly spring into existence before annihilating one another. These pairs are not real in the traditional sense, but their influence is real enough to shift the behavior of nearby fields. The virtual positrons are attracted to the real electron, while the virtual electrons are repelled, causing a rearrangement of charge density in the vacuum itself. This rearrangement slightly cancels out part of the electron's field at long range, effectively reducing the strength of the electric field, as seen from afar. But paradoxically, this means that the observed charge increases as you get closer, because the screening becomes less effective at short distances, revealing more of the electron's bare charge. This scale-dependent behavior, where fundamental constants shift with energy or proximity, is one of the most important insights of quantum field theory. The electric charge is not fixed. It runs, evolving subtly, depending on how close you get, or how much energy you probe with. And the reason it runs is vacuum polarization. This phenomenon doesn't just shift numbers. It reshapes our interpretation of reality. In quantum electrodynamics, the most accurate and predictive theory ever constructed, vacuum polarization is central to how interactions are calculated. The famous Feynman diagrams, which map out particle interactions through space and time, include loops that represent these virtual pair fluctuations. When we compute the probability of an electron scattering off another, or of a photon interacting with a charge, we must include the contribution of these loops. Because they aren't optional, the vacuum always participates. In fact, the agreement between QED predictions and experiment, verified to over 10 decimal places, hinges on accounting for this effect. Without vacuum polarization, you wouldn't correctly predict the anomalous magnetic moment of the electron, or the Lamb shift in atomic spectra, both of which have been experimentally confirmed. These aren't fringe curiosities, they are foundational features of quantum behavior, where the properties of empty space reshape what we measure as real. The vacuum is not passive, it is a participant in every interaction, a stage that talks back, a field that adjusts itself in response to presence. Perhaps even more profound is the way vacuum polarization hints at the dynamic nature of what we call constants. The fine structure constant, for example, a dimensionless number that determines the strength of electromagnetic interactions, appears to be a fundamental property of nature. Yet, under the scrutiny of vacuum effects, even this constant is not constant. Its effective value depends on the energy scale of the experiment, a phenomenon first observed in high-energy particle collisions, where deeper layers of the electron structure become visible. At very high energies, or extremely short distances, the effects of vacuum polarization diminish, and the true unscreened charge becomes more apparent. This scale dependence is a direct result of how the vacuum's virtual pairs respond to energetic probes. And this running of the coupling constant is not unique to electromagnetism. It appears in the strong and weak nuclear forces as well, helping to explain why the strengths of these forces change with context and perhaps even unify at incredibly high energies. In this way, vacuum polarization isn't just a correction to classical thinking. It's a mechanism for understanding how the universe's laws shift and evolve, depending on how closely you look. Even in cosmology, the implications of this phenomenon stretch wide. If space itself contains a built-in structure that can polarize and respond to energy and presence, then the vacuum might play an even more active role in shaping the cosmos than previously believed. While vacuum polarization by itself doesn't explain dark energy, it does reinforce the idea that empty space carries influence, pressure, and response capacity. And in exotic conditions, like near black holes, or in the early universe, these effects could become amplified, potentially altering the behavior of gravity, the propagation of light, or the evolution of structure. Some theories even speculate that in extreme gravitational fields, vacuum polarization could modify how photons travel, effectively making space behave like a non-linear optical medium. Though such effects are small, their theoretical possibility underscores a central lesson. The vacuum is not inert. It's more like a complex medium, fluid, reactive, and full of ephemeral fluctuations, that invisibly supports every law we observe. So when you picture nothingness, let go of the idea of still blackness or silent absence. Instead, imagine a seething storm of momentary particles, appearing and vanishing faster than any clock could measure, subtly altering the world even when no visible particles are present. Vacuum polarization is the proof that nature is never truly off, that zero is never truly zero, and that even the quietest spaces in the universe hum with activity. It is the reminder that every electric charge you've ever seen, every photon ever emitted, and every atom ever formed has done so not in isolation, but in conversation with the vacuum, its fields, its fluctuations, and its infinite, flickering possibility. Nothing is never empty, and from that, nothing, everything else is constantly, quietly being born. The four fundamental forces, and why there might be more. Before you learned about atoms, or energy, or even the shape of the universe, you knew something far more ancient. That some things fall, some things push, and some things pull. You may not have had the words for it then, but you could feel it. Gravity pressing your feet to the floor, muscles pulling against resistance, magnetism between two fridge decorations or a child's toy. These were not just random occurrences, they were the whispers of something deeper, the signatures of invisible frameworks that give order to everything that exists. And what might surprise you is that beneath all of modern physics, with its wild equations and complex particles, there are just four fundamental forces known to govern everything: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. That's it. Everything you see, touch, feel, and think is the result of these four interactions playing out on scales, both cosmic and subatomic. But just because we've named them doesn't mean we've truly understood them. And just because we think there are four doesn't mean there aren't more, quietly shaping reality from shadows we've yet to illuminate. Start with the most familiar: gravity. You feel it every moment of your life. It keeps planets in orbit, oceans pulled toward the moon, and galaxies spiraling in vast clusters. And yet, it's the weakest of the four. That sounds absurd, but if you've ever picked up a paperclip with a small magnet, you've already overcome the gravitational pull of an entire planet, using just a sliver of electromagnetic force. Gravity's strength comes not from power, but from persistence. It reaches infinitely far and acts on everything with mass. But here's the twist. In our best quantum theories, gravity doesn't quite fit. It refuses to be quantized like the other forces. Despite decades of effort, we still lack a working quantum theory of gravity, and we've never observed the hypothetical graviton, the particle thought to carry gravitational force. Gravity, in this way, is the outsider, obvious, omnipresent, and yet strangely uncooperative with the rest of physics. Then comes electromagnetism, the force of light, electricity, and magnetism. It governs the structure of atoms, the glow of the sun, the beating of your heart, and the firing of neurons in your brain. Electromagnetism is carried by photons, and unlike gravity, it plays beautifully with quantum mechanics. It is described by quantum electrodynamics, perhaps the most precisely tested theory in all of science. Yet this force, so elegant in theory and function, is also where quantum weirdness truly begins. Photons can interfere with themselves. Electromagnetic fields can exist in multiple states until measured. It is a force that reveals the duality of our universe, how something can be both a particle and a wave, both predictable and uncertain. The next two forces are less familiar but far more intense: the strong and weak nuclear forces. The strong force is the mightiest of them all. It binds quarks together inside protons and neutrons, and holds those protons and neutrons together inside atomic nuclei. Without it, atoms would fall apart instantly, and the universe would unravel into a sea of isolated particles. But the strong force is also the most confined. Its reach is incredibly short, less than the width of a proton. Yet within that domain, it overwhelms everything else. The weak force, by contrast, is responsible for radioactive decay and the fusion reactions that power stars. It's called weak only by comparison, but its role in converting one type of particle into another makes it a cornerstone of the universe's evolution. Through it, hydrogen becomes helium, and stars release their energy. Through it, unstable particles decay, creating neutrinos that stream through your body by the trillions every second, barely interacting, almost ghost-like. All four forces shape the universe in radically different ways. But here's where things get stranger. Physicists have long believed that these forces might not be as separate as they seem. In fact, we already know that electromagnetism and the weak force merge into a single force at high energies, a discovery known as Electroweak unification. It was once thought they were completely different. But when you zoom in far enough, when you recreate the conditions of the early universe, they are just two faces of the same entity. This idea raises a profound possibility. What if all four forces were once one? What if, in the earliest sliver of time after the Big Bang, there was a single unified force, splintered only later as the universe cooled and symmetry broke? This is the dream of grand unified theories, a single mathematical framework that explains all known forces except gravity. And then, perhaps even beyond that, a theory of everything, one that unites even gravity into the fold. String theory attempts this, suggesting that all particles and forces arise from vibrating strings in higher dimensional space. Other approaches like loop quantum gravity or causal dynamical triangulation take different routes, but they all chase the same ghost, a deeper order behind the forces we know. But the mystery doesn't stop there. Some physicists suspect there may be a fifth force, something that influences dark matter or dark energy, or the apparent inconsistencies in how gravity behaves at cosmic scales, a force that doesn't show up in particle accelerators, but may leave subtle traces in the way galaxies rotate or the way the universe expands. In recent years, experiments have hinted at possible anomalies, slight deviations in the expected behavior of particles or forces that could point to something new. One such anomaly emerged from studies of muons, heavier cousins of the electron. When placed in magnetic fields, muons wobble slightly differently than expected, suggesting that some unknown interaction may be influencing them. Is this a fifth force? A new particle? A crack in the standard model of physics? We don't yet know. But the fact that we are still asking these questions, still designing better experiments, still chasing shadows through colliders and cosmic background radiation, shows that the map of our universe is far from complete. And here's the most poetic part. The universe doesn't owe us answers. It doesn't need to explain why four forces exist, or why they seem so different, or why they may secretly be one. Yet it leaves breadcrumbs, patterns in starlight, symmetries in equations, anomalies in data. And we, the only known creatures to ask why, follow those trails not because we must, but because something in us refuses to accept mystery as the final word. You might think of the four fundamental forces as the grammar of reality, the rules that allow matter and motion to make meaning. But grammar is not the whole story. There is always subtext, nuance, and perhaps forces we have not yet learned to listen for. Maybe they are out there in hidden dimensions. Maybe they are right here, woven into the familiar, waiting for the right eyes to see. In the end, the story of forces is not a story of four, but of one, of unity fractured into function, of simplicity shattered into diversity. And if that sounds like a human story, perhaps it is. Because just like forces, we too contain multitudes, pulling, pushing, holding together and breaking apart, searching always for the symmetry that was once whole. The mystery of gravity's weakness. Why doesn't it dominate? Not everything that shapes your life is loud. Some forces whisper so quietly that their subtle pull is easy to overlook. Even when they sculpt the orbits of planets, govern the flow of time, and bind galaxies together, gravity, for all its cosmic authority, is by far the weakest of nature's fundamental forces, so astonishingly feeble that a simple refrigerator magnet can overpower the gravitational pull of the entire Earth on a paperclip. And yet, it is this same gravity that orchestrates the dance of celestial bodies, carves the structure of the universe, and anchors your feet to the ground. This paradox, that gravity is at once essential and absurdly weak, has puzzled physicists for generations. Why, if gravity is responsible for shaping the cosmos, does it pale in comparison to the other fundamental interactions. The electromagnetic force is 10 circumflex, 36 times stronger. The strong nuclear force holds atomic nuclei together with immense tenacity. Even the weak nuclear force, despite its name, is vastly more potent at short ranges. Gravity, by contrast, is fragile, diluted, and impotent at small scales, yet impossibly persistent over great distances. This contradiction, simple on the surface yet unresolved at the deepest theoretical levels, is known as the hierarchy problem. Why is gravity so much weaker than the rest? And why does it still matter so profoundly? To understand the roots of this enigma, you must first reconsider how gravity actually operates. Unlike other forces, which act through the exchange of quantum particles like photons or gluons, gravity, at least in its current form, is best described by the curvature of space-time itself. Mass and energy warp the fabric of space-time, and objects follow the curves this warping creates. In this geometric model, force is an illusion. What you feel as gravity is really inertia along a bent trajectory. This description, proposed by Albert Einstein in his theory of general relativity, has passed every experimental test to date, but it remains stubbornly incompatible with quantum field theory, which governs the other three forces with remarkable accuracy. The others live in a world of particles and probabilities. Gravity lives in a world of geometry and smooth continua. Reconciling these worlds has proven profoundly difficult, and one reason may be gravity's inexplicable weakness. If gravity were only slightly stronger, stars would burn out too quickly, planets might never coalesce, and the complexity necessary for life would not arise. But this observed weakness is not a calculated result. It is a fact of observation that cries out for deeper explanation. The smallness of Newton's gravitational constant is not predicted by the standard model. It is input, arbitrary, mysterious. Several theories attempt to bridge this gap by exploring whether gravity is truly weak or simply diluted. One compelling idea is the existence of extra dimensions, while the forces we're familiar with may be confined to the familiar 3 dimensions of space. Gravity might leak into additional spatial dimensions that are hidden from view. In such models, first proposed in the context of string theory, and later explored in large extra-dimension scenarios, gravity is not inherently feeble. It just spreads out into a larger arena. From our limited 3D perspective, we see only a faint residue of its true strength. This would not only explain gravity's comparative weakness, but also offer a pathway toward unifying gravity with quantum mechanics. Other approaches, like supersymmetry or theories involving gravitons, hypothetical quantum particles that would mediate gravitational interactions, attempt to quantize gravity directly and explain its small coupling constant as the result of symmetry breaking or vacuum dynamics. These models remain speculative, but they reflect a central truth. We do not yet know why gravity is so weak, and that ignorance is one of the biggest cracks in the foundation of modern physics. Even within our observable universe, gravity behaves in ways that amplify its mystery. Despite its weakness, it is always attractive. There are no negative gravitational charges like there are positive and negative electric charges. This ensures that gravitational effects accumulate. Every particle contributes, and their influence adds up without cancellation, over long distances and large scales. This is why gravity becomes dominant, not because it is strong, but because it never subtracts from itself. Meanwhile, other forces cancel out. Electric charges can neutralize. Nuclear forces are confined to short ranges, but gravity just keeps adding, inexorably, quietly. Its influence becomes overwhelming only when immense amounts of mass are involved. Planets, stars, galaxies. It's a slow builder, a patient sculptor of structure, and that very character is part of the reason it is hard to study in the lab. At the quantum level, gravity is almost undetectable. Its effects are so minuscule that even the tiniest electromagnetic fluctuation can drown them out. This makes direct experiments on quantum gravity incredibly difficult, requiring unprecedented sensitivity and isolation. Yet at the macroscopic scale, gravity becomes unignorable. It turns gas clouds into stars, stars into black holes, and black holes into the anchors of galaxies. It stretches light, bends time, and may even govern the fate of the universe. This apparent duality, utter weakness at the small scale, total dominance at the large, makes gravity uniquely fascinating. It does not interact with complexity in the same way other forces do. It doesn't hold atoms together, guide chemistry, or encode information in photons. Instead, it shapes the architecture on which all those interactions take place. It builds the scaffold, not the interior. This is why gravitational waves, ripples in space-time caused by massive accelerating bodies like merging black holes, took a century to detect. They required events of unimaginable scale to produce measurable effects. But once detected, they revealed that even the fabric of space-time can carry energy, information, and momentum. These waves confirmed predictions of general relativity and opened an entirely new window onto the cosmos. But they also emphasized how faint gravity is, how little it moves instruments, how vast an effort is required to hear its voice. That voice, however, carries stories from the earliest moments of the universe, when gravity may have played a central role in cosmic inflation, structure formation, and perhaps even in the emergence of time itself. Some physicists have even speculated whether gravity is not a fundamental force at all, but an emergent phenomenon, a statistical byproduct of the collective behavior of microscopic quantum systems. In this view, gravity arises in the same way temperature arises from the motion of molecules, not as a fundamental interaction, but as a large-scale pattern emerging from countless small interactions. This thermodynamic perspective on gravity, championed in various forms by researchers like Eric Verlinde, suggests that gravity's weakness may stem from its emergent nature, like the gentleness of a breeze that belies the frantic motion of individual air molecules. If gravity is not built into the universe at its smallest scales, but rather emerges from the distribution and entanglement of information across space-time, then its comparative softness might be a clue, not a bug, but a signpost to something deeper. These ideas are bold, underexplored, and not yet confirmed, but they represent the kind of conceptual expansion that may be necessary to truly grasp why the universe chose such a strange force to shape its largest patterns. So the next time you feel the weight of your body pressing into the earth, realize how faint that force truly is, how easily your muscles defeat it, how lightly it touches the particles inside you, yet how deeply it defines the shape of everything. Gravity is not weak because it fails to matter. It is weak so that complexity can emerge, so that stars do not collapse too quickly, so that time has room to unfold. It is a background rhythm rather than a spotlight, a soft hand that holds galaxies together without crushing the atoms inside them. Its weakness is not a flaw, it is the condition for stability. And the mystery of that weakness, still unsolved, is one of the great scientific invitations of our age, to question why the thing that governs the shape of all things is so easy to overcome, and what that paradox might be trying to teach us about what reality really is. Gauge bosons, the messengers of the universe's laws. What if I told you that the universe is not built on contact, but on correspondence, not on things colliding, but on silent agreements, faithfully exchanged across empty space? What if the forces you thought were pushes and pulls are actually negotiations, and every attraction, every repulsion, every influence is the result of a message passed between particles? An invisible whisper carried by something deeper than matter itself, beneath the fabric of your everyday experience, beneath the heat of sunlight, the hum of electricity, the magnet that clings to your fridge and the nuclear fusion powering the stars. There exists a hidden network of interaction. This network does not operate by touch. It communicates through messengers, quantum agents, that ferry information between fields. They are called gauge bosons, and they are the most silent yet essential participants in the grand conversation of existence. You don't see them, you don't feel them. And yet every heartbeat, every thought, every structure in the cosmos depends on their tireless work. They are the mediators of all the forces you know. Electromagnetism, the strong force, the weak force, even gravity itself. These particles do not make up matter. But they are what make matter matter. Without them, the universe would be cold, disconnected, inert. There would be no bonds, no energy exchange, no light. They are the lifeblood of interaction, the reason particles respond to each other, the mechanism by which reality remains coherent across space and time. To understand the role of gauge bosons is to abandon a classical worldview. In the Newtonian imagination, forces act across distance, gravitational pulls between planets, electrical repulsions between charges. But in the quantum world, action at a distance is replaced by interaction through exchange. All forces, no matter how familiar or strange, operate locally through the sending and receiving of specific quanta, packets of influence, tokens of interaction. Every field that fills the universe has particles, quantized ripples, that act as messengers. When an electron feels the presence of another, it is because a photon has been exchanged. When quarks cling together in the heart of an atomic nucleus, it is because gluons are constantly trading between them, forming a tangled, unbreakable web of color charge. Even in the realm of gravity, where Einstein's equations describe the bending of spacetime itself, physicists suspect a quantum messenger may exist, the graviton, a hypothetical gauge boson that would carry gravitational influence in the same way photons carry light. These messengers are not theoretical conveniences. They are necessary consequences of a deeper logic known as gauge symmetry. This principle, foundational in quantum field theory, asserts that the laws of nature must remain unchanged under certain transformations, changes in phase, in position, in orientation. To preserve this invariance, new fields must be introduced, and with those fields come particles. The symmetry requires enforcement. The bosons are that enforcement. Gauge symmetry doesn't just allow gauge bosons, it demands them. In electromagnetism, requiring that the quantum phase of a field can be changed locally without affecting physical predictions leads directly to the emergence of the photon. Its masslessness, its ability to travel at light speed, its universal role in electromagnetic interactions. All of it follows from the symmetry. It is not designed, it is inevitable. For the strong force, the symmetry is more complex, and gauge group that gives rise to not 1 but 8 gluons. Each gluon carries color charge and interacts not only with quarks but also with other gluons. This creates a self-interacting web of confinement, so intricate and chaotic that quarks are never found alone. The more you try to pull them apart, the more violently the gluons resist, generating new quark pairs from the vacuum, rather than allowing separation. This is not just a beautiful detail, it is a foundational principle of how the strong nuclear force operates. And it is why your protons and neutrons are stable, indivisible units of atomic structure. Without this force, and without the bosons that embody it, there would be no atoms, no elements, no chemistry. Compare that with the photon, which is massless, uncharged, and free to travel indefinitely, because it does not interact with itself. Light can propagate across the cosmos uninterrupted. You can see stars billions of light years away because their photons have been moving unhindered since long before Earth existed. That same interaction governs every electrical signal in your brain, every chemical reaction in your body. Gauge bosons are not just subatomic curiosities. They are the reason you see, feel, move, and think. Then there is the graviton, which, if it exists, would also be massless, but of spin too, allowing it to couple to all energy and momentum. It would explain how gravity, unlike the other forces, is universally attractive, shaping the fabric of the cosmos from black holes to the Big Bang. We haven't detected gravitons, and we may never be able to with current technology, but their mathematical role is undeniable. They complete the pattern. They fit the logic of how the universe should behave if every force has a messenger, and every interaction is an exchange. But this idea, that all interactions are carried out through messengers, extends even further. Some physicists believe that our known bosons may not be alone. There may be other messengers, other forces, other symmetries, operating in realms we cannot see. One such idea is the dark photon, a hypothetical cousin of the photon that might mediate forces in the dark sector, interacting with dark matter, which makes up most of the universe's mass, yet remains invisible to light. If it exists, the dark photon would imply a hidden gauge symmetry, a parallel rulebook that governs the unseen architecture of the cosmos. This is not science fiction, it is science in progress, logical extensions of the rules we already know. Similarly, grand unified theories propose that at extremely high energies, all the known forces were once one, unified under a larger symmetry group. In those moments after the Big Bang, exotic bosons may have existed, allowing particles to convert between types, shaping the matter-antimatter balance that determined the structure of everything that followed. These bosons would have vanished as the universe cooled, but their fingerprints remain. In the patterns of particles, the asymmetries in nature, the consistency of the forces we observe today. What makes gauge bosons so astonishing isn't just that they exist, but that their existence means the universe is not a static thing. It's a relationship, a structure of communication. Matter is real, but what gives it agency, what lets it move, bond, react, emit, absorb, is the ceaseless chatter of these messengers. Imagine the universe as a symphony where every note is a particle, but the music only emerges because of the rhythm, the timing, the structure, the exchanges that connect one note to another. Gauge bosons are that structure. They are the rhythm section of the cosmos. Without them, particles would remain isolated, unaware, inert. No two electrons would ever repel. No light would ever shine. No star would ever burn, and none of it would hold together, because there would be no forces to enforce the rules. Even the Higgs boson, although technically not a gauge boson, completes this picture. Its field interacts with other particles to give them mass, and in doing so, it breaks the Electroweak symmetry in a controlled way. This process is called spontaneous symmetry breaking, not because the symmetry vanishes, but because it is redefined. A new order emerges, and the universe settles into a new ground state. The photon remains massless, while the W and Z bosons become massive, differentiating electromagnetism from the weak force. Again, this transformation is enforced through messengers. The gauge bosons are the ones who carry the message of symmetry breaking and ensure its effects ripple through the quantum world. So when you reflect on the fabric of reality, consider that it is woven not from objects alone, but from the rules that connect them, and the particles that enforce those rules. Gauge bosons don't carry mass or structure. They carry principle. They are born from symmetry and live to preserve it. They do not seek recognition. They leave no footprints. And yet every aspect of your being depends on them. They are the custodians of consistency, the agents of natural law. The reason the same experiment gives the same result, no matter where or when you conduct it. They are the most disciplined, obedient, and essential entities in the universe. You might never sense them directly, but in every spark, every push, every heartbeat, their influence speaks through the dance of matter and motion. Gauge bosons are not just scientific ideas. They are philosophical reminders that order, not chaos, underlies the universe. That every force you feel is a conversation, and every conversation is a sign that something deeper is at work. Maintaining balance, enforcing harmony, upholding the elegance of physical law. Without them, the stars would go silent, the atoms would fall apart, the universe would be mute. But with them, everything speaks, quietly, constantly, and across the vastness of time and space. Yukawa forces, the forgotten link in particle mass. What if the key to understanding why particles have mass, why they are heavy, why they stick together, why atoms do not dissolve into a cloud of scattered quarks and electrons, lies not in the spotlight of modern physics, but in a nearly forgotten interaction, subtle and shadowed, that once bridged the gap between quantum forces and the structure of matter itself, long before the Higgs field became a household name in theoretical physics, and before gauge bosons were celebrated as the enforcers of cosmic law. There was another idea, a bold attempt to explain how matter holds itself together through an entirely different kind of force, one that emerged not from symmetries but from necessity, the Yukawa interaction. This concept, proposed by Hideki Yukawa in the 1930s, was the first successful theory to explain how the nucleus of an atom could remain stable, despite the electric repulsion between positively charged protons. Yukawa postulated that a new kind of particle, a massive mediator unlike the photon, must exist to glue protons and neutrons together through a short-range force, something that would act only over femtoscopic distances and vanish beyond them. This prediction led to the discovery of mesons, specifically pions, which act as the carriers of this interaction. But what makes Yukawa's idea so profound is not merely that it predicted a new particle. It introduced a new principle, a new kind of force that hinted at how mass could emerge from interaction, not just from intrinsic properties or field couplings. And though much of modern particle physics has moved on to more complex mechanisms, the Yukawa interaction remains a crucial piece of the puzzle, not just historically, but structurally. A mechanism still at work in the heart of every atom, in every breath you take, in every structure that resists disintegration. To understand what makes the Yukawa force unique, you must first step into the realm of the atomic nucleus. A realm where protons, despite all having the same positive charge, huddle tightly together inside a space 100,000 times smaller than an atom itself. Electromagnetism tells us that like charges repel, and by that logic, the atomic nucleus should explode from within, flinging protons apart in a violent storm of repulsion. But this does not happen. The reason lies in a hidden force stronger than electromagnetism at short distances, a force that holds protons and neutrons together like tightly bound dancers, resisting the urge to drift. Yukawa's insight was that such a force must be mediated by a massive particle, unlike the massless photon, which allows electromagnetism to act over infinite ranges. A massive carrier limits the reach of a force, making it vanish exponentially beyond a certain scale. Yukawa calculated that to explain the strength and range of the nuclear force, the mediator should have a mass around 200 times that of the electron. And remarkably, just years later, this particle was discovered in cosmic ray interactions, and later confirmed in particle accelerators. The pion, though not fundamental in the way photons or gluons are, pions arise from the deeper dynamics of the strong force, emerging as bound states of quarks and antiquarks. Yet their behavior is exactly what Yukawa predicted. They mediate the residual strong interaction between nucleons, acting like a shadow of the force that binds quarks within protons, extending its influence just far enough to hold nuclei together. What is especially compelling about Yukawa's theory is that it demonstrated, for the first time, how the mass of a force carrier shapes the nature of the force itself. This principle, now taken for granted, was revolutionary. In Newtonian gravity or classical electromagnetism, forces acted across space, instantaneously, or at least indefinitely. But Yukawa showed that if the mediating particle has mass, the force it carries is inherently local, limited in reach, and shaped by the mass of the mediator. This idea foreshadowed modern quantum field theories, where the properties of force-carrying bosons determine the strength, range, and behavior of the interactions they mediate. And it did more than that. It introduced a framework in which mass and interaction are inextricably linked. The potential energy associated with the Yukawa force takes the form of a decaying exponential, a mathematical signature of short-range attraction, and this form appears repeatedly in nuclear physics, particle scattering, and even effective field theories describing complex systems. In a sense, Yukawa did not just predict a new particle. He offered a way to visualize how force and mass entwine, how one defines the other, how particles can pull on each other, only if their messengers are slow enough to linger. And this interplay remains at the heart of many current questions in physics, including those involving the origin of fermion masses and the effective behavior of composite systems like nucleons and nuclei. But perhaps the most overlooked implication of Yukawa's force is what it teaches us about emergence, that some of the most fundamental seeming forces may not be fundamental at all, but rather residual effects of deeper dynamics. The nuclear force mediated by pions is not the original strong interaction, which operates at the level of quarks and gluons, but a leftover, a softened echo that operates between hadrons. It is the difference between a hand pulling a rope directly and a ripple that travels through a chain of knots. And yet, this echo is responsible for the stability of all matter. Without it, atomic nuclei would fly apart, stars would not shine, and chemistry would have no foundation. This reveals something quietly profound, that forces can emerge not from simplicity, but from complexity. That the residual behavior of a more intricate system can give rise to coherent, structured, and even life, enabling phenomena. Yukawa's force is such an emergent behavior, born from the strong interaction, yet manifesting in a domain that is no longer about quarks, but about protons and neutrons. And its form, range, and strength are determined not by arbitrary choice, but by the masses of the mediating pions. A direct link between mass and force, between what a particle is and how it influences others. Even in modern theories, the spirit of Yukawa's insight lives on. In the Standard Model, the term Yukawa coupling refers to the way in which fermions, like electrons and quarks, interact with the Higgs field, acquiring mass as a result. The strength of this interaction is not universal. Different particles couple with different strengths, which is why the electron is light and the top quark is heavy. These couplings are not yet explained by any deeper principle. We measure them, but we do not yet understand them. They are mysterious numbers written into the code of the cosmos, and they define the structure of everything we know. Why does the top quark couple so strongly, while the neutrino barely interacts at all? These questions remain open, and they trace their lineage directly back to Yukawa's original attempt to explain mass through interaction. He began with a force that required a mass to explain its range, and now we face the inverse. Masses that beg for an explanation through the forces they imply. It is a circle, a loop in logic that suggests a deeper unity yet to be found. A unity where mass, interaction, and structure are not separate concepts, but facets of the same principle. So what does this mean for your understanding of matter? It means that mass is not just something you have, it is something you feel, something you communicate, something that shapes the space around you and the structure of everything you see. It means that the particles in your body are not fixed entities, but nodes in a field of interaction, and that their very ability to bind, to endure, to resist change, is a consequence of forces like Yukawa's forces, that are subtle, short-lived, but utterly essential. It means that every atom in your body owes its coherence to a forgotten exchange, a fleeting interaction between pions and nucleons that plays out over distances smaller than a single femtometer, countless times each second, beneath your awareness, but within your reality. Yukawa's force is not merely historical. It is active, alive in the nuclei of every element, sculpting the periodic table, shaping the energy of stars, and enabling the formation of molecules, life, thought. It is the quiet architect of structure, the overlooked bridge between quantum mechanics and nuclear stability. And in this recognition lies a quiet lesson, that sometimes the most profound truths are not found in the newest theories or the brightest headlines, but in the enduring logic of ideas that were right all along. The forgotten link is not broken. It is foundational. And by remembering it, you remember something essential about what holds the universe together. Not just particles, but the bonds they share. The invisible links born from force, distance, and mass. Spontaneous symmetry breaking, when perfection fails for a reason. What if the deepest truths about the universe are not found in perfection, but in its collapse? When a flawless symmetry, elegant and balanced, suddenly fractures and gives birth to everything you see, feel, and are. It is tempting to think of nature as a harmonious machine, a symphony of laws obeyed without error, where every particle dances in obedience to symmetrical principles as old as time. But reality tells a stranger story. Beneath the structured fabric of the cosmos lies a surprising and powerful mechanism known as spontaneous symmetry breaking, a process in which the universe, though governed by symmetrical laws, chooses to manifest an asymmetric reality. This is not a flaw, but a feature. And without it, there would be no complexity, no diversity, no mass, no galaxies. Spontaneous symmetry breaking is the quiet rebellion that allows particles to differentiate, forces to separate, and fields to settle into uneven states that give rise to the richness of the physical world. It is not chaos overriding order. It is order choosing an outcome among infinite equals, and it is this subtle defiance, this creative fracture in an otherwise balanced system, that underpins some of the most profound phenomena in physics, from phase transitions in matter to the very formation of the structure in the early universe. To grasp this is to understand how perfection, when broken in the right way, becomes the architect of everything meaningful. Imagine standing a pencil perfectly upright on its tip. In theory, this arrangement is completely symmetrical. The pencil could fall in any direction with equal probability. But in practice, it always falls. The symmetry is perfect in the abstract, but unstable in reality. The moment the pencil tips, that symmetry is spontaneously broken, not because of a flaw in the laws of physics, but because reality must choose a direction. That chosen direction defines a new state, a new condition, one among many possible outcomes that were previously indistinguishable. This is the essence of spontaneous symmetry breaking. It is not imposed externally, like a hammer striking a sculpture. It arises internally, from the system's own nature, from its instability under perfect balance. In quantum field theory, this is not just a curiosity. It is the mechanism that determines the properties of particles, the shape of the vacuum, and the structure of interactions. The vacuum itself, the lowest energy state of a field, is not always symmetrical. In fact, it is often shaped by the very process of breaking symmetry, like a flat plateau, giving way to a valley, where a field rolls down to a specific point, not because it was forced there, but because the geometry of possibilities made one choice inevitable. The rules remain symmetric, but the outcome is not. One of the clearest manifestations of spontaneous symmetry breaking is found in phase transitions, something you witness every day without realizing its cosmic significance. When water freezes into ice, the liquid's continuous symmetry, where molecules move freely and uniformly, is broken as the molecules lock into a crystal lattice with a specific orientation. The laws of motion did not change. The system's energy landscape did. The same principle governs the behavior of magnets. Above a certain temperature, magnetic domains are randomly oriented, and the system has rotational symmetry. Below a critical temperature, these domains align and a preferred direction emerges. This chosen direction is not dictated by the laws themselves, but by the system settling into one of many possible equivalent ground states. The symmetry is still present in the governing equations, but it is hidden in the observed state. This concealment of symmetry, known as hidden symmetry, is not deception. It is the foundation of structure. In condensed matter physics, superconductivity and superfluidity also emerge from broken symmetries, where collective behaviors of particles form coherent phases that defy classical expectations. In each case, the system begins in a state of maximum symmetry and transitions into one where new properties, patterns, and interactions arise, not from added complexity, but from a single spontaneous decision made by the system itself. But the impact of spontaneous symmetry breaking stretches far beyond materials or phase changes. It reaches into the very fabric of the cosmos. In the earliest moments after the Big Bang, the universe is thought to have been in an ultra-high-energy state, governed by unified forces and perfect symmetry. As it cooled and expanded, This symmetry fractured in stages, breaking into distinct forces, particle families, and spatial structures. Each stage of breaking introduced a new order, a new hierarchy, a new layer of complexity. The forces we observe today, electromagnetism, the strong interaction, and gravity, may have once been indistinguishable aspects of a single symmetric force, their differences emerging only when the symmetry of the vacuum was broken. This cosmic choreography is not an accident. It is a consequence of fields evolving through an energy landscape that favored asymmetric solutions. The shape of this landscape, its hills, valleys, and ridges, determines what becomes massive, what remains massless, what binds, and what decays. The symmetry is not lost. It is hidden in the rules that still apply, even when their consequences appear unequal. And within this broken symmetry lies the reason why particles are not all the same, why matter has structure, and why the universe did not remain a uniform fog of undifferentiated energy. The consequences of symmetry breaking are also deeply embedded in the mathematical structure of particle physics. In many field theories, spontaneous symmetry breaking gives rise to what are known as Nambu-Goldstone bosons, massless particles that emerge whenever a continuous symmetry is broken. These bosons represent the degrees of freedom associated with the broken symmetries and play essential roles in low-energy physics. In the case of the strong interaction, for example, the approximate breaking of chiral symmetry gives rise to the light pions that mediate nuclear forces. These are not invented constructs. They are required outcomes of the symmetry structure itself. The process of symmetry breaking defines not only which particles appear, but how they interact, what their mass is, and how they decay. In this way, the vacuum of the universe, the supposedly empty background, becomes an active player, a structured medium that shapes the behavior of everything within it. It is not an absence, but a presence full of choice, encoded with the outcomes of broken symmetries and the echoes of decisions made in the first seconds of time. Spontaneous symmetry breaking also challenges our assumptions about cause and design. The fact that nature's laws allow for perfect symmetry, but reality chooses asymmetry, forces us to reconsider the difference between possible and actual. The equations might allow for countless identical outcomes, but something, a fluctuation, a quantum tremor, a tiny instability nudges the system into a particular direction, freezing it into a specific, measurable form. This selection is not the result of external will, but of internal inevitability, and this has philosophical weight. It means that structure, identity, even the very existence of distinction in the universe, comes not from an imposed blueprint, but from the delicate collapse of equivalence into preference. When symmetry breaks, a direction is born. When symmetry breaks, mass can arise, structures can form, and time can begin to move in a preferred direction. Even the arrow of time itself, the fact that the universe evolves from past to future, may be a consequence of early symmetry breaking, where uniformity fractured and entropy began its steady climb. This is why perfection is not the highest state in physics. Stability is not found in balance, but in its full creation. As it turns out, begins not in harmony, but in its silent, spontaneous violation. So the next time you look at the universe and wonder how its dazzling variety could emerge from the simplicity of laws, remember this: perfection failed, and that failure was the best thing that ever happened. Every galaxy, every star, every atom, every breath you take is the consequence of a symmetry that did not hold. But it did not vanish. It became the invisible scaffolding beneath the visible world. Spontaneous symmetry breaking is not destruction, it is differentiation. It is the quiet choosing of direction from a sea of possibility, the silent birth of structure from a vacuum rich with hidden rules. It is how the laws of physics remain the same, while the universe becomes new. And perhaps in your own life, in moments when balance collapses and certainty gives way to asymmetry, there is a deeper lesson whispered by the cosmos itself, that the breaking of symmetry is not a flaw, but the very source of individuality, change, and the future. Quantum tunneling forces, passing through the impossible. The world you know teaches you that barriers are absolute, that if an object lacks the energy to climb over a wall, it simply stops, bounces back, or waits until something changes. But deep beneath the surface of that familiar logic lies a truth that defies common sense and stretches the boundaries of what it means for something to be impossible. Quantum tunneling, a phenomenon in which particles pass through energy barriers they seemingly should never overcome. Not by force or collision, but by probability and presence, quietly slipping through the forbidden, as if the rules had loopholes no one told you about. In the classical world, the path of a particle is a traceable trajectory, predictable and determined by initial conditions. But in the quantum world, particles are described by wave functions, mathematical clouds of probability that don't just exist at a point, but extend into, and even beyond regions they're not supposed to enter. When these wave functions encounter a barrier, they don't vanish at the edge. They fade, penetrate, and sometimes reappear on the other side. This is not science fiction or a fringe idea. It is one of the most experimentally confirmed and practically useful effects in modern physics, explaining how stars burn, how atoms decay, and how cutting-edge technology peeks into the atomic world. Quantum tunneling is not rare, not exotic, and not optional. It is a foundational process baked into the logic of reality, one that reshapes what it means for something to be real, reachable, and relevant, even when every classical instinct says otherwise. To grasp tunneling is to accept that quantum mechanics does not play by the rules of classical cause and effect, but by probabilities shaped by the structure of space, energy, and boundary conditions. A particle's wave function does not stop abruptly at an energy wall. It decays gradually within it, like a whisper continuing inside a closed room. And if the wall is thin enough, or the particle's wavelength is broad enough, part of that wave function leaks through, carrying with it a small but non-zero chance that the particle will appear on the other side, even without the classical energy needed to scale the barrier. This is not a mistake or a breakdown in the laws of physics. It is how those laws actually operate at small scales. The mathematics behind it, rooted in the Sharp-Weidinger equation, shows that the probability of tunneling depends on both the height and width of the barrier and falls off exponentially with increasing size. But even when the odds are low, nature does not forbid, it simply measures. This is why particles trapped in unstable nuclei can escape, why protons in the sun can fuse, despite mutual repulsion, and why certain transistors and diodes work at all. Tunneling is not an anomaly. It is a path, quiet, subtle, but real. What makes quantum tunneling more than just a curiosity is how it serves as an engine for transformation across scales and systems. In nuclear decay, particles like alpha particles, helium nuclei bound tightly within an atom, should by all classical reasoning be stuck, unable to escape the strong nuclear binding that holds them in. But experiments show they do escape, and the rates at which they do so match precisely the predictions made by tunneling theory. The particle does not roll over a barrier, it tunnels through. Similarly, inside stars, where temperatures are immense, but still not high enough for protons to regularly overcome their electrostatic repulsion, fusion occurs anyway. Tunneling provides the path. Without it, stars would not shine, and heavier elements would not be forged in stellar cores. Your very existence depends on a process that seems on its surface impossible. And beyond cosmology, tunneling finds application in modern technology. Scanning tunneling microscopes, for instance, use the phenomenon to map surfaces atom by atom, exploiting the fact that electrons can tunnel across nanoscopic gaps, creating measurable currents that reveal the invisible landscape of matter. Tunnel diodes and Josephson junctions in superconductors rely on this same effect to allow or restrict current flow in ways classical circuits never could. In these devices, tunneling is not a defect, it is the function. But tunneling also carries conceptual consequences that ripple through your understanding of reality. It blurs the distinction between being and not being, between here and there. suggesting that presence is not binary but probabilistic. When a particle tunnels, it does not travel through the barrier in the usual sense. It does not accelerate, decelerate, or squeeze through. It appears, and this emergence is neither random nor willful. It is calculated, lawful, and repeatable, even though it defies intuition. Experiments have shown that tunneling can occur on timescales so brief. They challenge our notions of causality and speed, and yet they conform to conservation laws and do not allow information to travel faster than light. It is a paradox only if you insist on classical reasoning. In quantum mechanics, the act of tunneling is a shift in the probability distribution, a reallocation of existence, a demonstration that the universe does not ask whether something should happen, but only whether it might, and when that possibility exists. Even if vanishingly small, nature explores it. Even more fascinating is how quantum tunneling ties into the broader structure of physical law and cosmological evolution. In some models of the early universe, spontaneous transitions between energy states, such as from a false vacuum to a true vacuum, may have occurred via tunneling. These transitions could have triggered inflation, a rapid expansion that shaped the large-scale structure of the cosmos. Some speculative theories even suggest that entire new universes could tunnel into existence from a pre-existing vacuum, making tunneling not just a process within a universe, but a process that births universes. Though these ideas remain theoretical, they rest on the same principles that describe electron tunneling through a thin barrier in a lab. The same equations, the same math, the same logic. This continuity between the quantum and the cosmic, between the infinitesimal and the infinite, is not just mathematically elegant, it is philosophically humbling. It suggests that reality is stitched together by behaviors we can observe in one realm and extrapolate to another, that the bizarre is not confined to the tiny, and that possibility itself is a force. But tunneling also teaches a human lesson about effort, thresholds, and the invisible ways change occurs. Classical thinking tells you that effort must match obstacle, that without sufficient force, nothing can move. But the quantum world whispers something different, that even when energy seems insufficient, presence and probability can allow passage. That persistence does not always look like a hammer. It can be a haze that slips through cracks. In life, as in physics, not all barriers are walls. Some are thresholds waiting to be crossed by something small, quiet, and improbably patient. The particle does not need to break the wall. It needs only to exist in such a way that the wall no longer defines its limit. This is not metaphor, it is how the universe works. It does not need permission to move forward, only possibility. And sometimes, just barely, that is enough. So when you hear that quantum tunneling allows particles to pass through the impossible, know that it is not a fantasy or a loophole. It is a demonstration that nature is governed not only by what must happen, but also by what can. The particle tunnels, not because it breaks the rules, but because the rules are deeper than you thought. They account for chance, for gradient, for extension, beyond the expected. They allow particles to exist momentarily in places they could never reach by classical means. And in doing so, they allow stars to shine, atoms to form, and life to emerge. The impossible, it turns out, is only a measure of your assumptions. The universe, in its quiet elegance, keeps proving that sometimes the smallest things, given the right equations, can pass through anything. Anomalous forces, when theory meets weird reality. Sometimes the universe doesn't just whisper its mysteries, it throws them directly in our path, forcing us to admit that no matter how elegant our equations may seem, there are still forces at work we cannot yet explain. Phenomena that appear in laboratories and observations not as confirmation of theory, but as defiance of it. Anomalies that persist even under the most controlled scrutiny and dare us to reconsider what we thought we knew. And these are what physicists cautiously refer to as anomalous forces. Subtle deviations from predicted outcomes that cannot be brushed aside as error or noise. Forces that linger in the data like unanswered questions, hinting that beneath the surface of our established models, something deeper, stranger, and perhaps more profound, is unfolding. In a scientific world grounded in precision, reproducibility, and rigor, anomalous forces stand as both warning and invitation. Warning, because they expose the limits of current understanding. Invitation, because they point to the edge of discovery. These are not imaginary ghosts of pseudoscience, but real, measurable discrepancies that have haunted particle accelerators, gravitational experiments, and quantum systems alike, often resisting explanation, not because we lack imagination, but because the frameworks we trust most simply do not know what to do with them. One of the most striking examples comes from the precise measurements of the magnetic moment of elementary particles, particularly the muon, a heavier cousin of the electron. According to quantum electrodynamics, the behavior of such particles in a magnetic field can be predicted with extraordinary precision, accounting for even the tiniest quantum fluctuations of virtual particles that momentarily exist and vanish. Yet, when experiments such as the muon G-2 at Fermilab measure this magnetic property, they find a value that stubbornly refuses to align with the standard model of particle physics. The deviation is small, just parts per billion, but in a field where precision is paramount, that small mismatch is monumental. It suggests that something is influencing the muon's behavior that current theories do not account for. Perhaps a new force, an undiscovered particle, or a fundamental flaw in our equations. The implications are staggering. If confirmed with higher certainty, it would mean that the standard model, our best description of the subatomic world, is incomplete, not just in its known blind spots, like dark matter or gravity, but in domains we thought were well understood. This is the power of an anomaly. It is not loud, but it is persistent, and in its quiet resistance to being explained, it opens the door to revolutionary insight. Beyond particle physics, anomalous forces have also appeared in precision experiments involving gravity, forces so weak and subtle that only the most sensitive instruments can detect them, but which, once noticed, refuse to be dismissed. One such observation is the so-called fifth force, a hypothetical interaction beyond the four known fundamental forces: gravity, electromagnetism, the strong and the weak nuclear forces. Several experimental setups over the past few decades, particularly those involving ultra-sensitive torsion balances and atomic measurements, have reported minute deviations in the expected behavior of gravitational interactions under certain conditions. These are not dramatic, headline-grabbing results, but they are repeatable, structured, and deeply confusing. The notion of a fifth force is not without precedent. After all, each force we accept today once began as an unexplained effect. But what makes these findings truly anomalous is that they do not point to a single, clear new force, but rather suggest a family of possibilities. Forces that might only act at very short distances. Forces that might couple only to specific properties, like baryon number or lepton family. Or even forces that vary depending on cosmic background conditions. The deeper you look, the more the gravitational constant itself, long believed to be truly constant, starts to look like something that might be influenced by hidden variables we have not yet identified. And then, there are anomalies that arise not from what we observe in high-energy labs, but from what we do not observe in space. Cosmological puzzles that whisper of forces or interactions not captured by known theories. The accelerated expansion of the universe, attributed to dark energy, remains one of the most confounding such mysteries, while the standard cosmological model treats dark energy as a uniform, unchanging property of space-time. Observational data from supernovae, galaxy clusters, and the cosmic microwave background suggest inconsistencies, regional differences, time-dependent behavior, or even unexplained alignments, like the so-called axis of evil in the cosmic background radiation. These are not dramatic anomalies in isolation, but taken together, they hint at forces or principles influencing the universe on the largest scales in ways we do not yet comprehend. Could dark energy itself be a dynamical field rather than a constant? Could it be interacting weakly with matter in ways we have not accounted for? If so, then our current understanding of space-time structure formation and even causality, may need to be revised. In this sense, anomalous forces are not just quirks in data. They are cracks in the walls of a theory that has held for decades. Cracks through which entirely new paradigms might eventually pour. Even within quantum mechanics, the most tested and confirmed theory in the history of science, there are experimental results that hint at anomalous behavior. Certain systems display what is known as non-local correlations that go beyond what even standard quantum entanglement would predict. In particular, experiments involving massive quantum systems, macroscopic superconducting loops, Bose-Einstein condensates, or quantum optomechanical systems have occasionally produced results that stretch the boundaries of quantum decoherence and suggest the presence of couplings or influences not captured by standard Hamiltonians. These effects, while subtle and hard to reproduce, suggest that under the right conditions, the quantum realm may harbor interactions that deviate from our current mathematical treatments. Are these evidence of emergent forces that only appear at the quantum to classical boundary? Could they point to new sectors of physics where gravity and quantum mechanics begin to merge in unexpected ways? Or are they simply statistical noise masquerading as mystery? The point is not that we have the answers, but that the data keeps asking the question. And when data asks repeatedly, you have to listen. What makes anomalous forces especially important is not just that they challenge theory, but that they often appear at the intersection of existing frameworks. Where gravity meets quantum mechanics, where particle physics meets cosmology, where statistical behavior meets determinism, they are signs that the boundaries between our categories may be blurrier than we thought, and they often emerge not from seeking the new, but from examining the old with unprecedented precision. History shows us that many breakthroughs in physics began this way. The precession of Mercury's orbit, which eventually led to general relativity, the blackbody radiation problem, which gave rise to quantum theory, the Michelson-Morley experiment, which shattered the ether model and opened the door to special relativity. Each of these began as an anomaly, as a discrepancy between expectation and observation. Theories did not collapse overnight, but they were forced to evolve. And today, anomalies in magnetic behavior, gravitational coupling, cosmic background asymmetries, or decay rates that fluctuate with solar activity could very well be the precursors of tomorrow's revolutions. Anomalous forces, then, are not detours from the scientific path. They are the path. They are how the universe taps us on the shoulder and says, "Look again." They demand humility because they show that even our most cherished theories are not sacred. They are provisional, models that fit until something better comes along. And they demand courage, because to investigate anomalies seriously is to risk finding out that your tools, your language, and your assumptions might all need to change. But that is how science grows. It does not discard the past. It absorbs, refines, and deepens. And anomalies are the leverage points where refinement begins. Whether through unexpected shifts in neutrino oscillations, strange asymmetries in beta decay, or odd fluctuations in measurements of fundamental constants, the universe is constantly offering clues, not always easy to interpret, but always worth pursuing, because at the end of that pursuit lies not just a better theory, but a clearer understanding of what kind of reality you truly live in. So the next time you hear of an experiment that doesn't quite fit, or a force that seems to act without clear cause, resist the urge to dismiss it as an outlier. Ask what it might mean if it's real. Ask what kind of universe allows such a thing to occur. Because somewhere in those mismatches between theory and observation, between prediction and data, lies the edge of what we know. And just beyond that edge, waiting patiently in the shadows of our ignorance, are the new forces, the new rules, and the new stories the universe is ready to tell. Anomalous forces are not errors. They are openings. They are not obstacles. They are invitations. And if we have the curiosity to explore them, we might discover that the weirdness of reality is not its exception, but its signature. Zero-point energy, the eternal motion in stillness. Stillness, as you know it, is an illusion. Because even in the deepest silence of space, in the coldest vacuum humanity can imagine, in a volume entirely emptied of matter, stripped of all light and heat and movement. There remains something undying, something irreducible, something that cannot be stopped, zero-point energy, the eternal motion woven into the very fabric of nothingness. While the classical picture of a vacuum implies perfect stillness, no particles, no fields, no vibrations, the quantum reality is profoundly different. In quantum mechanics, even empty space is a seething landscape of fluctuating energy, a restless background hum that never quite goes silent. This is not a poetic metaphor, but a measurable phenomenon, rooted in the Heisenberg uncertainty principle, which tells us that no particle or field can ever be pinned down with absolute precision, not even to a state of zero energy. Because of this, even in the ground state, the lowest energy configuration possible, quantum fields continue to jitter, oscillate, and breathe with a kind of invisible life. These fluctuations are not theoretical curiosities. They manifest physically as observable forces, such as the Casimir Effect, where two uncharged metal plates, placed close together in a vacuum experience, a measurable attraction caused by the differences in zero-point energy between the inside and outside of the gap. The force arises not from any classical interaction, but from the vacuum itself, because the plates restrict the wavelengths of the quantum fields between them, altering the vacuum energy locally and generating a push. What looks like nothing is not nothing at all. It is a stage teeming with possibility, with motion that never ceases, even when all else has stopped. Zero-point energy is not confined to isolated experiments. It permeates all of space, filling the universe with a background energy that paradoxically cannot be fully extracted or neutralized. In quantum field theory, each mode of a field contributes a small amount of this zero-point energy, and since space allows for infinitely many such modes, the total energy appears infinite. This infinite result is, of course, unphysical and must be renormalized away in many calculations. But the residue of this energy is real enough to have profound implications. For instance, one of the biggest mysteries in modern physics is the cosmological constant problem. When theorists attempt to calculate the vacuum energy density based on quantum field theory, the result is more than 100 orders of magnitude larger than what is observed in the accelerating expansion of the universe. That discrepancy is not a minor error. It is perhaps the largest mismatch between theory and observation in the history of science. A reminder that zero-point energy is not just strange, but deeply consequential. It suggests that the vacuum, the so-called nothingness of space, is not just a passive emptiness, but an active player in cosmic evolution. Whether this energy contributes to dark energy, or whether some unknown mechanism cancels it out, almost perfectly remains one of the greatest open questions in physics. What's clear, however, is that the vacuum is anything but empty. It is dense with unseen dynamics, forever resisting true stillness, and defying our best attempts to silence its pulse. This ever-present motion has implications far beyond cosmology. In atomic and molecular systems, zero-point energy plays a crucial role in determining stability and behavior. Take, for example, the helium atom. Because of its low atomic mass and the persistent presence of zero-point energy, helium does not solidify under normal pressure, even near absolute zero. The quantum fluctuations are enough to keep the atoms moving, preventing them from locking into a crystalline structure. Similarly, the ground state of the quantum harmonic oscillator, a fundamental model in physics, still contains energy even at its lowest point. This zero-point energy is not removable, not suppressible, and not optional. It is embedded in the uncertainty of quantum systems. You might think of it as the eternal heartbeat of existence, a baseline rhythm that never flatlines, ensuring that even in the most extreme stillness, something is always happening. These vibrations underpin chemical bond structures, influence transition rates, and contribute to phenomena such as tunneling and spontaneous emission. In a sense, zero-point energy forms the quantum floor beneath all matter and energy, an invisible bedrock of instability that paradoxically provides coherence and structure. technological implications of zero-point energy have long intrigued scientists and futurists alike. The idea that one could somehow tap into this ubiquitous sea of energy has inspired everything from legitimate research into vacuum fluctuation manipulation to far-fetched claims of limitless free energy. However, extracting useful work from zero-point energy is far more complex than it sounds. The fluctuations are symmetric, meaning that any local gain is matched by an equal loss elsewhere. Preserving the overall balance attempts to harness this energy must confront the thermodynamic restrictions that prevent perpetual motion machines. Still, the dream persists. Not because it is easy, but because the concept invites us to rethink our relationship with energy, space, and the limitations we assume are fixed. More plausibly, scientists are exploring how controlled manipulation of vacuum states, such as in squeezed light fields or quantum electrodynamics cavities, can lead to new technologies in quantum computing, ultra-sensitive measurements, and even exotic propulsion methods. These efforts do not aim to extract raw power from zero-point energy, but to shape the vacuum's behavior to perform useful tasks. A more nuanced and achievable goal that still feels like science fiction made real. What's more, zero-point energy challenges your very understanding of what nothing means. It suggests that nothingness is an illusion, a linguistic placeholder for what lies beneath detection. In quantum terms, empty space is always busy. It is filled with virtual particles popping in and out of existence, with electric and magnetic field lines flickering unpredictably, with tiny momenta that cancel on average, but never quite reach zero. This isn't metaphysical, it's measurable, and it forces a profound reconsideration of the boundary between being and non-being. If every point in space harbors motion, potential, and energy, then perhaps existence itself is more granular and less binary than we assume. This view opens a door to reinterpreting the origins of the universe, the conditions before time, and the substrates of consciousness itself, not with speculative mysticism, but with a scientific humility that acknowledges how little we truly know about the foundations of reality. So when you imagine a place completely devoid of matter, light, and temperature, what physicists call the vacuum, do not picture silence, picture vibration, tension, and restlessness. Picture a stage with no actors but a booming orchestra beneath the floorboards. Zero-point energy is the inescapable motion that haunts even the stillest spaces, the unrelenting background rhythm that persists no matter how much energy you extract, cool, or isolate. It is not noise. It is the baseline, not error, but essence. It is the reminder that stillness, like so much else in the universe, is never absolute, only relative, only apparent, only ever one step above the fundamental hum that never stops playing. The fine structure constant, a number that controls everything. There exists a number, neither whole nor arbitrary, neither created by us nor fully explained by theory, that quietly governs nearly every interaction you have ever experienced, from the colors emitted by stars to the structure of atoms, to the very chemistry that sustains your life. And yet, this number is not found in any object, but woven into the laws that define all objects. It is the fine structure constant, a dimensionless value close to 1/137, simple in appearance, but profound in consequence, a single ratio that somehow determines the strength of electromagnetic interactions, and therefore influences the shape, behavior, and existence of everything that responds to light. While most physical constants come with units, meters per second, joules per Kelvin, the fine structure constant, usually denoted by the Greek letter alpha, is pure stripped of measurement, a ratio that exists outside our chosen scales. It combines three other constants: the elementary charge, Planck's constant, and the speed of light, into a single unitless quantity that expresses how strongly charged particles interact with each other through the electromagnetic field. And what's most astonishing is not just that this number appears in so many places, but that its value seems neither dictated by theory nor derived from deeper principles. It simply is, appearing in equations like a fingerprint the universe left behind without explanation. To see just how central alpha is, consider the hydrogen atom, the simplest system in quantum mechanics, a single electron bound to a proton. The fine structure constant dictates the splitting of its energy levels, the subtle shifts in spectral lines observed when light is emitted or absorbed. Without alpha, these fine details, the fine structure of atomic spectra, would vanish, collapsing the delicate complexity of atomic behavior into something blunt and oversimplified. The colors of neon signs, the spectral fingerprints of distant stars, the glow of heated gases, all depend on the tiny corrections governed by this constant. But its influence does not stop there. The probability of an electron scattering off a photon, the cross-section of particles in quantum electrodynamics, the coupling strength in the most precisely verified theory in history, all are governed by alpha. And remarkably, the calculated predictions of quantum electrodynamics agree with experiment to more than 10 decimal places, making it the most successful theory ever developed. All thanks to this mysterious ratio quietly shaping the parameters. Yet for all its usefulness, alpha remains one of the greatest puzzles in modern physics. Not because we don't understand what it does, but because we don't understand why it has the value it does. If alpha were slightly different, say 1/135 or 1/139, the universe would not just look different, it might not function at all. A slightly stronger alpha would tighten the grip between electrons and nuclei, altering the sizes of atoms, destabilizing molecules, perhaps making chemistry as we know it impossible. A slightly weaker alpha would loosen that grip, and electrons might fly too freely, rendering matter diffuse, inert, or incapable of forming the complexity required for life. Even nuclear reactions in stars would behave differently, changing the abundance of elements like carbon and oxygen, fundamentals of biology. This precarious balance has led many to consider alpha in the context of the anthropic principle, which suggests that the constants of nature are not random, but finely tuned for life to exist. Whether this reflects a deeper truth, a selection bias from a multiverse, or something entirely beyond our comprehension, alpha sits at the heart of the question. It is not merely a number in physics. It is a pivot point of possibility, a silent architect of structure, stability, and subtlety in the universe. What makes alpha even more intriguing is its unchanging nature, at least as far as we can tell. For decades, scientists have tested whether this constant is truly constant, probing light from distant quasars, examining the spectra of ancient stars, and measuring the properties of fundamental particles over time to detect any variation. So far, results are mostly consistent with constancy, though a few tantalizing hints have emerged suggesting slight variation across vast cosmic distances, implying that the constant may not be truly universal after all. If confirmed, this would imply that the laws of physics themselves might evolve with time and space, adding a dramatic layer to our understanding of nature's foundations. But even if alpha is stable across the cosmos, its origin remains a mystery. It's not predicted by the standard model. It's not derived from first principles. It is inserted into the equations because it works, not because we understand its necessity. This suggests that either we are missing a deeper layer of physics where alpha is calculated, or we are living in a universe whose laws are contingent, shaped not by absolute necessity, but by the quiet roll of cosmic dice. Theories beyond the standard model, such as string theory or grand unified theories, attempt to embed alpha into a larger framework, often suggesting that at high energies or in higher dimensions, the apparent constants of our low-energy world emerge from more fundamental relations. In some of these theories, the value of alpha is tied to the geometry of hidden dimensions or the dynamics of compactified fields, suggesting that what we see as fixed might be the shadow of a higher reality. Others explore the idea that alpha runs with energy. The effective strength of the electromagnetic interaction changes slightly depending on the energy scale at which you measure it. This running has been observed in particle colliders, and plays a crucial role in the unification of forces at extremely high energies. But again, even with these insights, the actual low energy value of alpha, why it lands so precisely near 1/137, remains elusive. It is a boundary we cannot yet cross, a known unknown that silently reminds us of how much we still do not understand about the very framework in which physics operates. Perhaps the most poetic aspect of alpha is that it connects the seemingly disconnected. It binds together constants from different realms, Planck's constant from quantum mechanics, the speed of light from relativity, and the elementary charge from electromagnetism. In doing so, it serves as a bridge between disciplines, an encoded whisper of unity in a fragmented picture. It shows up in the equations of quantum electrodynamics, yes, but also subtly appears in areas ranging from solid-state physics to cosmology, guiding how photons interact with charged particles and how atoms transition between states. In certain speculative models, the value of alpha might even encode information about the entropy of the universe, or the holographic limits of information density. And yet, this profound number remains dimensionless and unadorned, just a pure ratio, unconnected to any particular unit system, immune to redefinition by measurement standards. It is not of our making, but of nature's choosing, and in that purity lies its mystery. So the next time you glance at a light bulb, gaze at the stars, or ponder why atoms hold together the way they do, remember that beneath all those phenomena lies a simple, stubborn number that quietly choreographs the steps. The fine structure constant is not loud or visible, but it is foundational, a hidden ruler by which the universe measures its interactions. And though we have named it, used it, and built technologies upon its precision, we do not yet know why it is what it is. It is the heartbeat of light, the fingerprint of charge, and the unresolved riddle in the center of our most precise equations. A number that controls everything and answers to no one. Why the weak force is actually crucial for life. You might never notice it. You might live your entire life without feeling its presence. But somewhere in the deepest interior of stars, in the nuclei of atoms, and even inside your own body, a force is working silently, not with brute strength or commanding reach, but with a kind of delicate precision that makes life, as we know it, not only possible but inevitable. This force is often dismissed as the weakest of nature's interactions, a title that almost sounds insulting when compared to gravity's sculpting of galaxies or the electromagnetic forces that bind matter together. But this so-called weak force is not weak in significance. It is subtle, and in that subtlety lies the key to some of the most essential transformations in the universe. Without it, the stars would burn differently, or not at all. The elements in your body would never have been forged. Radioactive decay would halt, neutrinos would be meaningless, and evolution, as shaped by the mutation of DNA through weak, mediated processes, might never have had a path to walk. To understand the importance of the weak force is to peer into the engine room of the cosmos. Not the grand external motions of celestial bodies, but the inner chemistry of nuclear alchemy, where identities shift, where particles become other particles, and where balance is restored not through destruction, but through delicate transmutation. Unlike the other fundamental forces, which bind, attract, or push, the weak force transforms. It's the force of change. It's the mechanism that allows one flavor of matter to become another. And this simple ability, this quiet rearrangement of nature's alphabet, is what allows the cosmos to evolve. Deep within stars, hydrogen atoms must eventually become helium if they are to shine. But that transformation requires a proton to morph into a neutron, a feat gravity cannot demand, electromagnetism cannot enforce, and the strong nuclear force cannot permit. Only the weak force can do it. It is the signature of stellar birth and stellar death, and therefore the origin of heavier elements. Carbon, oxygen, iron, all the way up to the gold in your rings and the iodine in your blood. This means that every breath you take, every cell you divide, Every trace element you absorb through your food is part of a chemical story whose punctuation marks were set by the weak force billions of years ago. And its role doesn't end with the stars. Here on Earth, the weak force mediates a particular kind of decay, beta decay, that allows radioactive elements to transmute, emitting electrons and neutrinos in the process. While often feared for its association with nuclear fallout, this decay is a natural part of Earth's heat and radioactive balance, the inner warmth of our planet, which drives plate tectonics, volcanic activity, and perhaps even provided the thermal stability needed for life to form in the first place, owes itself in part to these slow, persistent nuclear whispers. But go even smaller, even more intimate, and you'll find the weak force participating in the mutation of DNA. Because ionizing radiation, whether from space or Earth's crust, changes nucleotides, induces errors, and occasionally triggers the kind of genetic variation that fuels evolution. Without mutation, there is no adaptation. Without adaptation, no biodiversity. Without biodiversity, no life as we see it. No trees, no birds, no breath. This means that the weak force is, in a way, the invisible hand that nudges biology forward, one decay at a time. It is the architect of novelty, but perhaps its most mysterious fingerprint lies in the realm of the neutrino, an elusive, nearly massless particle that rarely interacts, yet floods the cosmos by the trillions. These particles, born from weak interactions, are ghostly messengers of nuclear events, from the center of the sunday to the remnants of supernovae. Their constant flight through space tells the story of matter's transformation, of energy released, of balance restored. But more than that, the study of neutrinos has revealed something astonishing. They oscillate. They change type mid-flight, and this behavior hints at physics beyond our current understanding, suggesting that the weak force might be the doorway to deeper truths about the universe, about why there is more matter than antimatter, about why time seems to flow in only one direction. Indeed, the weak force is one of the few known phenomena that distinguishes between past and future, while gravity, electromagnetism, and even the strong nuclear force play their roles without caring whether time moves forward or backward. The weak force does not. It has a handedness, a preference. It introduces a subtle arrow into the universe's equations, giving direction to entropy, to causality, to history. This temporal asymmetry may hold the key to some of the deepest questions in physics. So while it's easy to think of it as weak, because its influence is confined to tiny scales and fleeting moments, its reach is vast in consequence. It doesn't move mountains, but it helps stars burn. It doesn't shape your body, but it allows your atoms to be born. It doesn't command attention, but it quietly rewrites the script of nature, one transformation at a time. And because it operates in such quietude, so few people stop to ask, what would the world be without it? There would be no fusion in the sunday, no radioactive decay, no natural sources of heat in planetary cores, no neutrino messengers from distant galaxies, no heavy elements, no diversity of particles, no possibility of chemistry evolving beyond hydrogen and helium, no Earth, no complexity, no life. In that silence, in that absence, you begin to hear its importance. The weak force is not about strength. It's about subtle necessity. It is not obvious, but it is essential. It is not constant, but it is catalytic. And perhaps this is its greatest gift to the universe, to make transformation possible without demanding attention, to reshape what is into what could be, to whisper, not shout, and still leave behind the architecture of stars, the foundation of planets, and the restless creativity of life. Supersymmetry's hidden forces, waiting in the shadows. What if every particle you've ever known, every electron orbiting an atom, every quark building the heart of matter, every photon traveling from star to eye, was only half the story, and for each one there existed a hidden counterpart, a partner not yet seen but theoretically essential, waiting silently in the shadows of our universe, completing a symmetry so perfect and profound that it could unify the fragmented forces of nature, stabilize the quantum vacuum, and even explain the invisible scaffolding of galaxies? This is the promise of supersymmetry, a bold extension of our understanding of reality that suggests every known particle has a superpartner. For every fermion, a boson; for every boson, a fermion. This symmetry isn't just elegant. It is functional, proposed not for aesthetics, but to resolve deep problems that the standard model of particle physics leaves unanswered. Supersymmetry, or SUSY as it's often called, offers a framework in which the strong, weak, and electromagnetic forces might unify at high energies, where quantum corrections to particle masses no longer spiral into infinities, and where a candidate for dark matter naturally emerges, not as an added guess, but as a built-in feature. Yet, despite decades of searching, these superpartners remain elusive, and with each passing experiment that fails to find them, the tension between the elegance of the idea and the stubbornness of reality grows sharper. To appreciate why supersymmetry is so compelling, you have to look at the problems it tries to solve. Chief among them, the hierarchy problem. In quantum field theory, particles like the Higgs boson receive corrections to their mass from all other particles they interact with, including virtual particles that exist fleetingly in the quantum vacuum. These corrections should push the Higgs mass up toward enormous scales, far beyond what is observed. Without a mechanism to cancel or balance these contributions, an immense amount of fine-tuning is required, so much that many physicists believe there must be a deeper reason. Supersymmetry provides that reason. If every particle has a superpartner with the same charge but different spin, the quantum corrections from each pair neatly cancel out. This elegant cancellation stabilizes the Higgs mass, keeping it at the Electroweak scale, and making our universe's structure possible. But SUSY does more than that. It predicts a convergence of the three fundamental force strengths at high energy, a unification that the standard model narrowly misses. In SUSY extensions, the forces elegantly merge, suggesting a deeper simplicity behind the apparent complexity of particle interactions. The theory doesn't just answer one question, it answers several at once, making it one of the most attractive candidates for physics beyond the standard model. Moreover, supersymmetry offers a ready-made explanation for dark matter, the unseen mass that outweighs visible matter in the cosmos and holds galaxies together with its gravitational pull. In many SUSY models, the lightest supersymmetric particle, often a neutralino, is stable, electrically neutral, and interacts weakly, precisely the properties needed for a dark matter candidate. Unlike speculative particles, added purely to explain astronomical observations, SUSY's dark matter emerges naturally from its structure, making it an economical theory, solving both particle physics and cosmology with the same set of tools. These hypothetical particles could have been produced in the early universe, remaining today as relics from the Big Bang, drifting silently through galaxies, and perhaps even passing through your body right now, undetected. Particle detectors around the world are built to look for them. And yet so far, none have been conclusively observed. The absence of detection doesn't disprove supersymmetry, but it forces theorists to adjust the scale, suggesting that if SUSY exists, it might be realized at higher energies than we expected, or in more subtle, broken forms. Indeed, one of the key ideas within supersymmetry is that the symmetry must be broken, because we do not observe superpartners with the same mass as their counterparts. If an electron and a selectron, its hypothetical bosonic partner, had identical masses, we would have seen both long ago. This means the symmetry must be broken in such a way that the superpartners are heavier, hidden from current detection capabilities. The mechanism of supersymmetry breaking remains an open question. Various models propose different dynamics, from gravity, mediated breaking, to gauge, mediated or anomaly, mediated processes. Each version predicts different mass spectra, decay chains, and phenomenology, guiding how we build experiments and interpret data. Large Hadron Collider experiments have probed deeper into these territories, tightening the constraints, but not yet closing the door. The hope is that with higher energies, greater luminosity, or more sensitive detectors, we might catch a glimpse of Susie's hidden zoo. Gluinos, squarks, leptons, and neutralinos. Echoes of the familiar, refracted through an unseen symmetry. Yet the deeper allure of supersymmetry lies not just in its ability to solve technical problems, but in the philosophical shift it implies. It proposes a world in which matter and force are two sides of the same coin, unified by symmetry rather than separated by category. This challenges the long-standing distinction between particles that build matter and those that mediate interactions, suggesting a deeper level where that distinction fades. In such a world, the difference between an electron and a photon is not categorical, but symmetrical, transformable under a hidden operation that reshapes the identity of particles. If true, this would revolutionize our understanding of what particles are, pointing toward a universe where what you see is just one slice of a richer, more balanced framework. It would also bring particle physics closer to a unified theory of everything, possibly harmonizing with string theory, which requires supersymmetry for mathematical consistency in 10 dimensions. In this way, SUSY is not just a fix for existing problems. It's a step toward a more fundamental vision of nature. Still, the lack of experimental confirmation has forced a reckoning. As data accumulates and no superpartners emerge, some physicists begin to question whether the theory's elegance is enough. Others dig deeper, exploring more complex versions of SUSY, like split supersymmetry or minimal supersymmetric standard models, that might still elude detection while preserving key benefits. The community remains divided. Some believe SUSY will eventually show itself with the right tools. Others pivot toward alternative theories, like extra dimensions, technicolor, or quantum gravity approaches. But even among critics, the influence of supersymmetry is undeniable. Its mathematical elegance, its deep implications, and its explanatory power have shaped decades of thinking, training generations of physicists to see symmetry not as an optional detail, but as a foundational principle. So as you look out into a universe governed by forces you can feel but not always see, remember that there may be another layer still, an unseen symmetry whispering beneath the known, offering balance where there seems only division, and hinting that the particles we've discovered are merely one face of a deeper dual reality. Supersymmetry may not have shown itself yet, but it remains one of the most captivating stories in theoretical physics. A possibility that the universe is more symmetrical, more unified, and more complete than our current models suggest. And that somewhere, just beyond the reach of our detectors, its hidden forces are still waiting to be found. Fifth force hypotheses. Could there be one more? What if the 4 fundamental forces you've been taught to accept as complete, gravity, electromagnetism, the strong and the weak nuclear interactions, are not the full set, but merely the visible pillars of a larger unfinished framework? And lurking, just beyond the threshold of our current measurements, there exists a 5th force, subtle and selective threading between particles, not with brute strength, but with elusive intent, hiding in anomalies, resisting detection, yet refusing to go away. For decades, physicists have entertained this possibility, not as fantasy, but as a scientific suspicion fueled by small inconsistencies, strange data, and theoretical gaps that no existing force fully accounts for. While the standard model has proven astonishingly accurate in describing known particles and interactions, it leaves many mysteries unsolved. Why gravity is so weak, what dark matter is, whether neutrinos have unexpected behaviors, and why certain physical constants are so finely tuned. These cracks in the model have led some to ask, what if another force exists? One that doesn't fit neatly into current categories, one that interacts with only some types of particles, or only at specific distances, or only under rare conditions. And what if we've already seen glimpses of it without realizing? The search for a fifth force began with the realization that known interactions don't fully explain the behavior of matter under all conditions. In the 1980s, a group of scientists reported that gravity appeared to be slightly weaker or stronger, depending on the composition of the materials involved. A violation of the equivalence principle, which states that gravity should affect all masses equally regardless of their makeup. Although those results were eventually ruled inconclusive, they sparked decades of increasingly precise experiments designed to test the inverse square law of gravity, hoping to detect deviations at small scales where a new force might emerge. These experiments, involving torsion balances and atom interferometry, have pushed the boundaries of sensitivity, placing tighter constraints on how any fifth force could behave, but not ruling it out entirely. In some cases, hints have appeared in measurements of atomic transitions, where tiny shifts in energy levels suggest the influence of an unknown interaction. In others, large-scale astrophysical observations have shown irregularities in galactic rotation curves, or in the motion of stars that don't neatly align with standard gravitational predictions. Though often attributed to dark matter, these discrepancies could, in principle, point to a fifth force acting subtly across cosmic distances. Theoretically, a fifth force could take many forms. It might be mediated by a new boson, a particle akin to the photon, gluon, or graviton, but one that couples selectively, perhaps only to leptons or neutrinos, or to hypothetical dark sector particles. Some models propose protophobic forces, interactions that ignore protons, but affect neutrons or electrons, providing a possible explanation for anomalies seen in nuclear decay experiments. Others suggest that the fifth force might be connected to dark matter itself, serving as a mediator between visible and invisible sectors of the universe. This could explain why dark matter interacts gravitationally, but not electromagnetically. Perhaps it is governed by its own force, one that only weakly leaks into the visible world. In such scenarios, the fifth force might be incredibly weak, or have a very short range, or only manifest in high-energy environments, or under specific alignments. The possibilities are wide-ranging, but bound by the same scientific rigor. The force must respect existing data while offering an explanation for what the other four cannot. One particularly intriguing experimental hint came from a Hungarian research group studying nuclear transitions in beryllium-8. In 2016, they reported an unexpected excess of electron-positron pairs emitted at a specific angle during the decay, a signal that could suggest the presence of a new boson with a mass around 17 mega-electron-volts. This hypothetical particle, dubbed the X17 boson, would be the carrier of a fifth force, one that doesn't fit into any known interaction. While independent confirmation is still needed, the same group later reported a similar anomaly in helium-4 transitions, suggesting a consistent pattern. If real, the X17 would be the first particle discovered beyond the standard model that carries a force. An astonishing breakthrough. Critics remain cautious, noting that nuclear experiments are notoriously complex and prone to systematic errors. But the fact that multiple observations align, and that the potential boson's properties are theoretically plausible, keeps interest alive. Major laboratories are now working to replicate the results. And while nothing has been conclusively verified yet, the possibility remains tantalizing. What would the discovery of a fifth force mean for physics? It would fundamentally reshape our understanding of nature's architecture. It could provide a bridge between quantum mechanics and gravity, or help explain the matter-antimatter asymmetry in the universe. It might even offer new insights into the mysterious dark energy accelerating the expansion of the cosmos. From a practical standpoint, identifying a fifth force could open up new technologies, just as electromagnetism led to electronics and quantum mechanics to semiconductors. Even if the force proves too weak to harness directly, its mere existence would signal a new layer of physical law, one that adds nuance, depth, and possibility to our understanding of what interactions are possible in nature. It would also suggest that our current view of the universe, while effective, is still incomplete, and that the simplicity of 4 fundamental forces is a story still being written. Skeptics rightly ask, why haven't we seen it yet? If it's real, the answer lies in the nature of such a force. It may be shy, selective, or subtle in ways our instruments were not designed to detect. It may hide in data already collected, waiting to be seen through a new lens, or it may emerge only in specific contexts, early universe conditions, certain atomic configurations, or interactions involving particles we don't normally study. Like all great scientific shifts, its discovery would require not just better tools, but sharper questions, the willingness to look again where we thought the answers were settled. The fifth force, if it exists, would not rewrite everything, but it would extend the canvas, giving us a richer portrait of how nature truly works. So the next time you think of gravity holding you down, or of magnets sticking to your fridge, remember, those are only part of the picture. The forces you know may not be the only ones at play. In the quiet edges of the atom, or in the long shadows between galaxies, there could be another force whispering its influence. Subtle, rare, but real. The universe has never claimed to be finished, and the search for a fifth force is a reminder that behind every law we've learned may lie another law, waiting not to break the old ones, but to complete them. The weak nuclear force, the power behind radioactive decay, underneath the skin of every object, behind the surface of every stable thing you see. There's a trembling, invisible force, quietly rewriting the rules of matter. One that doesn't build, or bind, or hold together, but instead causes things to fall apart. Not through violence, but through subtle transformation. This is the weak nuclear force, and its name is misleading. Not because it lacks importance, but because its power is strange. Unlike gravity, which pulls everything together, or electromagnetism, which sparks life into electronics and lightning alike, the weak force works in shadows, operating inside atoms, rearranging identities, and triggering the quiet decay that fuels the engines of stars and the clocks of radioactive time. It governs beta decay, where a neutron spontaneously transforms into a proton, an electron, and an antineutrino, an event so gentle you'd never know it was happening, unless you had the tools to listen. And yet, this microscopic flicker is responsible for some of the most important transformations in the universe. Without it, the sun wouldn't shine. Carbon wouldn't form in stars. Life, in the chemical way we understand it, would not exist. The weak force doesn't just allow for change. It is change, sculpting matter at the quantum level, by permitting certain particles to become others, flipping their identities like the pages of a well-practiced script that only the universe can read. It operates through the exchange of massive particles, Wu and Z bosons, which are unlike the massless photon of electromagnetism, and it's their mass that makes the weak force short, ranged and rare, but also deeply consequential. While the strong nuclear force binds quarks into protons and neutrons, the weak force slips between the cracks, creating pathways for transformation that otherwise wouldn't occur. It's the reason nuclear reactors generate heat. It's the mechanism behind radioactive dating. It's the spark of neutrino emissions that pierce through your body by the trillions every second without notice. And it's a reminder that not all power is visible, not all energy is loud. Some of the most profound changes are quiet, invisible, and constant, operating far beneath the thresholds of our perception. Until you learn to see what they're doing and realize you've been surrounded by transformation all along. The weak force also reminds us that nature doesn't treat matter as fixed or sacred. Identity itself is fluid in the subatomic world. A down quark can become an up quark. A neutron can decay into a proton. Particles can change type, shedding mass or charge in the process, like nature playing with the very definition of what it means to exist. And this is no small thing. The weak force violates symmetries we once believed were fundamental. In particular, it breaks something called parity, meaning it behaves differently if you reflect a system in a mirror. This was once thought impossible, as if nature should never prefer left over right. But the weak force does. It's asymmetric, it chooses. And this shattered a deeply held belief in the symmetry of physical laws. The experiment that revealed this, Qin-Shung Wu's cobalt-60 decay study in 1956, was one of the most shocking in physics history. It showed that the universe has a handedness, that the laws of physics are not the same in a mirrored world. In a sense, the weak force plays favorites. That's not poetry, that's measurement. It altered our understanding of the universe's balance, hinting that even the cosmos might contain an intrinsic bias. And this ties into even deeper mysteries, like why there's more matter than antimatter in the observable universe. Because when we recreate the Big Bang's conditions in particle accelerators, we get equal parts of matter and antimatter. And yet, when we look at the sky, we don't see annihilation everywhere. We see stars, planets, life made of matter. So where did all the antimatter go? One of the leading suspects is the weak force. It violates a combination of symmetries, known as CP violation, that allows for the slight preference of matter over antimatter in the early universe. That tiny imbalance, amplified by time and expansion, may be the reason anything exists at all. Without this imperfection, we'd have ended up with a universe of pure light, empty, sterile, silent. So here's the paradox. The weak force is weak, by name and strength, yet possibly the only reason we're here to talk about it. It's the origin of imperfection, the root of cosmic bias, the whisper that pushed us off the edge of nothingness and into form. And while it works on the tiniest scales, changing the flavor of quarks, enabling nuclear fusion, sending neutrinos flying, it has shaped galaxies, not with force, but with imbalance, with favor. With asymmetry that tilted the scales just enough for existence to win, neutrinos, the ghostly children of the weak force, are perhaps the strangest messengers of this process. They almost never interact. They pass through light, years of lead without a trace, and yet they carry information from the most violent and mysterious processes in the cosmos. Supernovae, neutron-star collisions, even the heart of the sun. When a supernova explodes, 99% of its energy is released as a burst of neutrinos, streaming through space at nearly the speed of light. We can't see them, but they're the real signal, and they owe their very existence to the weak force. You live in a constant stream of neutrinos. Trillions pass through your body every second, whispering stories of fusion and collapse from deep space. The fact that they exist, so ghostly, so inert, reminds us that the weak force is not merely about decay. It's about communication, about change, about escape. These particles are born when matter undergoes a subtle shift, when identity is no longer static, and their flight is a map of where change happens in the universe. It's humbling to realize that without the weak force, there would be no nuclear fusion in stars. Hydrogen would never become helium. Energy would not be released in the sun's core. That warm morning light you take for granted is the product of proton fusion, an interaction mediated, again, by the weak force. It's not just abstract physics. It's the reason your planet isn't frozen. The reason chlorophyll can trap photons. The reason evolution had time to play. Every living thing owes its existence to a process that hinges on the ability of protons to change identity. That ability belongs solely to the weak interaction. Without it, the universe would still be hydrogen, cold, dark, lifeless. So how can such a quiet, short-ranged, almost invisible force be so crucial? Because its power lies in what it permits, not what it resists. The weak force is not about dominance. It's about possibility, transformation. It opens doors, rearranges the furniture of particles, and allows matter to flow between identities. It doesn't hold atoms together or push galaxies apart. It changes the cast of reality itself, one decay at a time. And it does this not constantly, but precisely. The probabilities are calculable. but never deterministic. It's a game of chance with cosmic consequences. It's how uranium becomes lead, how potassium becomes calcium, how a star collapses under its own weight and briefly outshines an entire galaxy. Every ticking Geiger counter is a song of the weak force. Every fossil dated with carbon-14 tells a story that begins with a neutron deciding to become something else. And in each of these transformations, a little mystery leaks into the world. A reminder that nothing stays as it is, not even the building blocks of matter. So the next time you think of change, of decay, of endings, remember this: some forces don't destroy, they evolve, they reassign. They allow the world to reconfigure itself, not through explosion, but through patience, through identity shifts, through the quiet possibility of becoming. The weak nuclear force is not dramatic, it's not flashy, but it is the keeper of transformation. And perhaps that's the real definition of strength. Not resistance, but evolution. Not control, but release. Not holding on, but letting go so something new can begin.